When we think about space, we usually imagine it stretching endlessly outward. But what if the real mysteries lie above and below us? In this journey, we'll chart the vertical dimension of our solar system, from the fierce gamma-ray storms rising over the galactic north to the cold gravitational corridors drifting beneath our orbit. This is more than a map of the stars. It's a scan of our cosmic altitude. Welcome to what lies above and below our solar system. The galactic North Pole, mapping the top of our solar system. Picture yourself floating high above the solar system and looking down from a place that isn't on Earth. Of course, there is no such thing as up in space, but scientists do talk about the galactic North Pole. However, it is one of the most important points of reference in the galaxy, even though it doesn't have many stars or other cosmic lights. We know which way is above us in the Milky Way by looking at the galactic North Pole. Figuring this out can help us with everything from navigating satellites to knowing how our galaxy is put together. So what exactly is it? The galactic North Pole is the point in the sky that lies 90 degrees above the plane of the Milky Way. If you imagine the Milky Way as a giant, thin disk, like a cosmic vinyl record, then the galactic North Pole is the direction pointing straight out from that disk, perpendicular to its plane. Earth's own North Pole is tilted with respect to the Milky Way, but the galactic version provides a stable, universal up that astronomers use to chart the cosmos. It's located in the constellation Coma Berenices, a relatively faint patch of sky not far from the better-known Leo constellation. But why does this matter? Because space is not a chaotic jumble of stars. It's highly structured, and direction matters. When astronomers map the motion of the solar system, the orientation of other galaxies, or the gravitational pull of mysterious forces like the Great Attractor, they need a fixed frame of reference. The galactic North Pole gives them that. It allows us to describe our position within the galaxy not just in terms of longitude and latitude, but in 3 full dimensions: pitch, roll, and yaw, just like a spacecraft. To find the galactic North Pole, scientists use the galactic coordinate system, which is kind of like the latitude and longitude system we use on Earth, but for the sky. In this system, the Milky Way's plane is the galactic equator, and the galactic North Pole lies at coordinates 0 degrees plus 90 degrees. By pointing telescopes in this direction, astronomers can observe what's happening above the galactic disk, away from the crowded band of stars and dust that obscures much of the Milky Way's interior. That's when things get interesting. There is a thin layer of galaxy fog that you can see through when you look up at the galaxy North Pole. The area is mostly free of gas and dust, which makes it a great place to see into the very deep sky. In this direction, some of the farthest galaxies and quasars ever seen have been found. It's not an accident. That's one of the best ways for light to get to us without being swallowed or spread out. Observations in this direction have helped astronomers understand the structure of the Milky Way's halo, a massive diffuse region of dark matter, gas, and ancient stars that surrounds the galaxy like a ghostly bubble. It's through measurements taken above the galactic plane that we've confirmed the halo is far larger than the Milky Way's visible disk. Without the galactic North Pole as a reference point, mapping that halo would be far more difficult. The area is also critical for studies of cosmic microwave background radiation, the afterglow of the Big Bang. To get clean measurements, telescopes like WMAP and Planck point toward regions with minimal galactic interference. Guess where one of the cleanest spots is? That's right, near the galactic North Pole. It's like staring into deep time from the top of our galactic perch. Even gravitational wave astronomy is beginning to make use of galactic orientation. The distribution of detectors on Earth and the interpretation of signals from space can depend on knowing precisely where we are within the galactic framework. Events like black hole mergers and neutron star collisions don't just happen randomly. They can be tied to regions of high mass density, which in turn can be mapped relative to the galactic poles. And as the solar system continues its slow drift through the galaxy, circling the Milky Way's center once every 230 million years, our orientation relative to the galactic North Pole changes. It's a cosmic dance on a grand scale, and understanding our position now helps scientists model where we came from and where we're going. It's amazing how this idea of an unseen thing, just a point in the sky, helps hold our whole picture of the galaxy together. From maps between stars to trips to the farthest reaches of space, the galactic North Pole gives us a sense of where we are in space. We would still be lost in the Starsea, trying to figure out which way is up without it. What's physically located above the Sun's North Pole? What would you find if you could rise straight up above the North Pole of the Sun, past the atmosphere, past the planets in rotation, and into the void beyond? Don't think of this as a thought experiment. Experts in space, missions, and astrophysics have spent decades studying the Sun, cosmic probe data, and models of our local space environment to try to find an answer to this real question. Above the Sun's North Pole is the solar polar region, an area of intense magnetic activity and dynamic plasma behavior. Unlike the Sun's equator, where sunspots and solar flares are common, the poles are quieter, but not inactive. During solar minimum, the Sun's magnetic field lines extend straight out from the poles into space, creating high-speed solar winds that stream outward like invisible rivers of charged particles. These particles form part of the heliospheric current sheet, a warped, spiraling structure that fills the solar system with solar magnetic influence. The Ulysses spacecraft, launched in 1990, gave us our first ever close-up look at the Sun's polar regions. It flew over both poles in the 1990s and early 2000s, revealing that the polar solar wind is faster, less dense, and more uniform than the wind emitted near the equator. This fast wind contributes to shaping the overall heliosphere, a vast bubble that surrounds the entire solar system and acts as a shield against galactic cosmic rays. So in a very real sense, the space above the Sun's North Pole is an energetic gateway pushing charged particles and magnetic waves outward into interstellar space. But if you go higher, past Pluto's orbit, you'll reach the outer heliosphere. This is where the Sun's power starts to fade. This area above the North Pole of the Sun is still full of high-energy protons and electrons from the solar wind, but there are a lot fewer of them. The Sun's magnetic field is made up of long, twisted lines that interact with the magnetic field between the stars. Voyager 1, which left the heliosphere in 2012, showed us what's out there, but it left close to the northern edge of the heliosphere. In terms of the galaxy, it did go above the North Pole of the Sun. Beyond the heliosphere lies the local interstellar medium, LISM, a sparse mix of gas, dust, and cosmic rays drifting between stars. The Sun is currently traveling through a cloudlet called the local interstellar cloud, a region of slightly warmer, denser interstellar gas. The properties of this cloud affect how the heliosphere is shaped, squeezed, or extended in certain directions. Interestingly, because of the Sun's relative motion through space, the heliosphere is thought to be compressed on its front side and elongated behind it. The nose of the heliosphere, the direction the Sun is moving, actually points slightly above the solar system's mid-plane, not far from the Sun's North Pole. That means many of the particles and fields encountered in deep space missions actually come from this above direction. As you ascend even further, the view opens to the galactic environment. The space above the Sun's North Pole provides one of the clearest lines of sight out of the dense plane of the Milky Way. The thin distribution of interstellar dust in this direction allows astronomers to peer deep into the universe with minimal interference. Telescopes like the Chandra X-ray Observatory and Planck have used this clean viewing angle to study background radiation, distant galaxies, and high-energy X-ray sources. The directionality of cosmic rays, the strange, fast particles that come from deep space and hit Earth, is another interesting finding. Studies show that these cosmic rays are not spread out in a completely even way. There might be a small amount of directional anisotropy, with some entry trends leaning more toward the galactic north. Even though we don't fully understand why, This is another sign that the space above the North Pole of our Sun may be busier and more organized than we thought. In a way, this area is also a transition corridor, a place where the galaxy's impact starts and our star's stops. There are parts of it that are neither ours nor foreign. As people send more probes beyond the solar system, like the Interstellar Probe mission idea that NASA is currently studying, these spacecraft will probably move in the same ways that Voyager did, up, out, and north, in search of the unknown that lies beyond the pole. The solar apex, where the Sun is really headed. We often forget that the Sun is moving through the sky at an amazing speed, even though the planets and the Moon are moving around it. This movement isn't a fluke, it moves along a clear path, and the way our Sun is going at the moment is called the solar apex. This isn't just a fact from astronomy books, it helps us understand where we are in the Milky Way and how gravity affects the whole solar system. The bright star Vega in the constellation Lyra is close to where the Sun's peak is located. This is in the direction of the constellation Hercules. This movement isn't just a straight line through space. There are many worlds around the Sun, and they all circle the center of the Milky Way. The Earth goes around once every 230 million years. As part of this trip, our solar system moves through the galaxy at a speed of about 828,000 kilometers per hour, which is about 514,000 miles per hour. This motion means that if you were to look at the sky from outside the solar system over hundreds of thousands of years, you would notice a slow, steady drift of our position. The solar apex marks the direction of that drift. Everything in the solar system is being pulled that way, carried like a cosmic passenger train along invisible tracks defined by gravity and the mass distribution of the galaxy. The path toward the solar apex cuts slightly above the plane of the galaxy, which gives it vertical significance. It's one of the key reasons why the northern region of the Heliosphere, the vast bubble surrounding the Sun carved out by solar wind, is thought to be shaped differently than its southern counterpart. Because the Sun is moving forward and upward in galactic terms, the leading edge of the Heliosphere is compressed like the front of a boat cutting through water, while the trailing side stretches out into a long tail. This forward motion also creates what is known as the nose of the Heliosphere. Voyager 1 exited near this direction, providing valuable data about how the solar wind collides with the interstellar medium at the front of our galactic journey. The Interstellar Boundary Explorer, IBEX, and other missions have helped map this region, revealing complex interactions between charged solar particles and interstellar magnetic fields. The solar apex plays a crucial role in cosmic ray exposure as well. As we travel toward Hercules, we are plowing into streams of high-energy particles from the galaxy. The Sun's magnetic field and the surrounding heliosphere act as a shield, but it's constantly tested by the conditions at the solar apex. This is where the cosmic weather can be most intense, and where studying incoming particle flow helps scientists refine models of how galactic forces affect our solar system. Understanding the solar apex isn't just useful for space weather prediction or deep space navigation, it also helps scientists chart our solar neighborhood. By comparing the Sun's velocity to nearby stars, astronomers can identify stellar associations, moving groups, and the structure of our local arm in the galaxy. It's how we know that our solar system resides in the Orion Arm, a minor spiral structure between the Sagittarius and Perseus arms. The fact that the Sun isn't moving by itself is very interesting. It brings with it the local interstellar cloud, LIC, a cloud of gas and dust between the stars. We are going through this cloud right now, and its features, like temperature, pressure, and particle density, change the way the heliosphere forms around us. The fact that we're going deeper into this cloud could change how safe we are from radiation from other galaxies in the future. Another thing to think about is the chance of seeing thicker clouds ahead. Models of nearby interstellar regions have shown that we may leave the LIC and join a colder, thicker cloud in a few thousand years. If that happens, the heliosphere could get much smaller, letting more cosmic energy into the solar system, and possibly changing the temperatures of the planets. Knowing the solar apex is important for spaceship guidance, especially for journeys that go beyond the solar system. It figures out the best ways for probes to leave the solar system. Voyager, New Horizons, and the planned Interstellar probe are all aiming for paths that are aligned with or close to the Sun's apex, so that they can gather as much information as possible about the edge of our star's impact and the galaxy beyond. High-energy cosmic rays entering from above. Beyond the soft glow of stars and the pull of planets' gravity, space turns into a battlefield full of bullets that can't be seen. Cosmological rays are these bullets. They are made up of very high-energy particles that move through space almost as fast as light. Some people are born in the centers of stars that are bursting. Some of them come from places we don't fully understand yet. And a lot of them, they're coming from above. Cosmic rays aren't rays in the traditional sense. They're charged particles, mostly protons, with some heavier atomic nuclei and a small percentage of electrons. They arrive at Earth from all directions, but there's a noticeable concentration from above the solar system's ecliptic plane. The exact reason for this isn't fully known, but it's tied to the structure of the galaxy, the Sun's magnetic field, and the shape of the heliosphere, which acts as our protective bubble. The heliosphere plays a massive role in modulating cosmic rays. As these particles enter from interstellar space, they encounter the solar wind and magnetic fields that surround the Sun. Depending on the phase of the solar cycle, this invisible shield is either strong or weak. During solar minimum, when the Sun is quiet, the shield is weaker, allowing more cosmic rays to penetrate into the inner solar system, including those entering from above the Sun's North Pole. Spacecraft like Voyager 1 and 2 have been key in studying this phenomenon. Voyager 1, which exited the heliosphere near the northern edge, encountered a steep rise in cosmic ray intensity, an indication that it had entered a region where galactic radiation is no longer blocked or slowed by the Sun's magnetic influence. The directionality of these rays, many coming from above, suggests that there may be structural anisotropies in the galaxy's magnetic fields, or that we're moving through a cosmic ray headwind. Ground-based monitors and balloon tests, like those done in Antarctica, add another piece to this puzzle. A strange trend has been picked out by these instruments. More cosmic ray impacts are happening above Earth's polar areas. This has to do with the Sun's magnetic field once more. Charged particles move along the lines of a magnetic field, and the field is designed so that the poles make it easier for rays to reach them. The Earth's magnetic field then pushes these particles toward the poles, which makes auroras and other natural phenomena that look like the rapid landings. There's also a class of cosmic rays called ultra-high-energy cosmic rays, UHECRs, that defy easy explanation. These are the most energetic particles we've ever detected, millions of times more energetic than anything created in Earth's particle accelerators. Some of them appear to come from directions above the plane of the Milky Way, with no clear source in sight. One theory is that they originate from active galactic nuclei, supermassive black holes, or even gamma-ray bursts. But no one knows for sure. Efforts to trace their origin are ongoing. Projects like the Pierre Auger Observatory and NASA's AMS-02 Alpha Magnetic Spectrometer aboard the ISS are mapping cosmic ray directions with increasing precision. The AMS, in particular, is sensitive to the trajectory of incoming particles and has detected a slight excess in positrons, antimatter counterparts of electrons, coming from above the ecliptic. That's led some to speculate about dark matter annihilation, or previously unknown astrophysical processes occurring just beyond our current observational limits. Cosmic rays are both interesting and dangerous because they can go through things. They can go through the shells of spaceships, people, and even technology. This is a big worry for future trips to deep space, especially those that will go beyond Earth's magnetic field. Radiation shielding gets bigger and more complicated, and engineers can make better spaceship materials and orientations by knowing the patterns of incoming radiation. In the end, the cosmic rays that fall from the sky are a steady warning that space is not empty. It's tense, moves quickly, and is often aggressive. But by studying them, we also learn something very important: how to look beyond the solar system's edges and find the signs of disasters that happened millions or even billions of years ago. North Galactic Spur, the dusty bridge over our heads. A huge winding structure has been studied by scientists for decades, but most people have never heard of it. It lies above the plane of the Milky Way and looks like a faint ghost across the sky. At radio and X-ray wavelengths, it's one of the most interesting and noticeable things in the sky. It's called the North Galactic Spur. It curves around the Sun like a huge dusty bridge, linking parts of the galaxy's inner disk to its outer ring. Plus, no one is really sure what it is. The North Galactic Spur is massive. When observed in radio waves, it appears as a long, curving filament that rises above the plane of the Milky Way and then bends back downward. It begins near the galactic center and stretches across a huge swath of the northern sky. In visible light, it's hard to detect due to the dust and gas that blocks our view. But in polarized light, especially in microwave and X-ray wavelengths, it glows brightly, making it a key feature in many sky surveys. Some scientists believe it's part of a superbubble, a shell of gas and dust blown outward by multiple supernova explosions that occurred near the center of the galaxy. These powerful explosions could have launched material in an arc above the galactic disk, creating a loop-like structure that we now see as the spur. If this is true, then the North Galactic Spur is not just a visual artifact, it's the lingering scar of ancient stellar violence. Others think it comes from a more nearby place. It could be a structure in the local bubble, which is the area of hot, charged gas with low density that the solar system is currently moving through. The spur might be a leftover from events that happened close to the Sun in the past. It could be from a group of nearby stars that went supernova in the last few million years. In this case, the branch would look more like a bubble wall than a bridge between black holes. Some models suggest it could be a combination of both, a local structure superimposed on a more distant galactic feature. This idea complicates efforts to map it in 3 dimensions. When astronomers observe the North Galactic Spur, they're looking through multiple layers of gas and dust, all moving at different speeds and located at different distances. Untangling these overlapping signals is one of the big challenges in understanding what the spur actually is. It has significant implications for cosmic microwave background (CMB) research. The Planck and WMAP missions, which mapped the faint afterglow of the Big Bang, had to account for foreground contamination, microwave radiation coming from our own galaxy that could interfere with readings of the early universe. The North Galactic Spur is one of the biggest sources of that contamination. Its strong polarized emission can distort sensitive measurements unless properly filtered out. This has also made it a target of interest for dark matter studies. Some scientists once thought there might be a signal of dark matter annihilation coming from the galactic center. But when anomalies appeared in the data, it became clear that some of those signals were actually due to structures like the spur, not dark matter itself. In other words, misunderstanding what's above us can lead to false assumptions about the entire universe. The spur's intersection with Earth's magnetic field lines is another interesting feature. When you look at polarization maps, you can see that the dust grains in the North Galactic Spur are lined up with the magnetic fields of the galaxies. This makes them emit polarized light. This has given researchers a unique look at how magnetic fields behave on galactic sizes, which is famously hard to study directly. And yet, for all the effort that's gone into understanding it, the North Galactic Spur remains strangely unresolved. It doesn't behave like a simple arc, nor does it fit neatly into existing models of galactic structure. It might be a coincidence of perspective, an unusually shaped dust cloud, or something much larger that we're only beginning to grasp. Future missions with improved 3D mapping capabilities, like the upcoming SphereX mission, may finally be able to pinpoint the spur's true distance and structure. The local bubble's upper boundary, our superheated shell. Our solar system doesn't move through space by itself. It sails through the local bubble, a big bumpy hole in the space between the stars. A series of strong supernovae millions of years ago blew this bubble into life. It is a huge area of low-density, high-temperature plasma. We've known about the local bubble for a long time, but we're still making maps of what's above the solar system and at the top of it. That shell above us that is very hot may be much more complicated and important than anyone thought. To understand this, think of the local bubble as a huge bumpy bubble that is about 1,000 light-years across. At the moment, our Sun is inside it, slightly off from the center. Interstellar gas and dust that are cooler and thicker make up the walls of the bubble. The inside is filled with hot, thin plasma that is about 1,000,000 degrees Kelvin hot. The shock waves of dead stars shape this environment, making a space area that is remarkably clear compared to the normal cosmic cloud. What lies above the solar system in this bubble is not simply more emptiness. It's a gradual transition to those denser outer regions. As you rise vertically from the plane of the solar system, particle density begins to increase. This isn't uniform. The bubble's structure is lumpy and asymmetrical. The upper boundary, located in the galactic north, is thought to interface with neighboring bubbles and clouds, such as the Lupon superbubble, a colossal region also formed by ancient supernova from the nearby Scorpius-Centaurus star association. These overlapping shells have created ripples and turbulence that continue to affect the structure above our solar system. The boundary is not static. It's dynamic, warping and shifting as interstellar forces interact. One of the ways scientists study this upper region is through soft X-ray background radiation. The hot plasma inside the bubble emits X-rays, and by observing how those emissions are absorbed or blocked, astronomers can estimate the distance and thickness of the outer shell in different directions. Data from space telescopes like ROSAT and XMMM Newton have revealed that the bubble's northern edge is thinner than in other directions. This suggests we may be approaching the edge of the local bubble, or even breaching into a new environment. Some astronomers believe we are moving toward the denser region of the local interstellar cloud, LIC, and that our journey might soon push the Heliosphere into uncharted interstellar territory. When it comes to shaping the Heliosphere, this high limit is crucial. As the solar wind moves further away, it will finally hit the gap between the stars. The density and pressure of the surroundings affect where this exchange takes place. The heliosphere is squished in the direction of the bubble's upper edge, where the pressure between the stars is changing. This causes an imbalance. Voyager 1, which left the heliosphere from the north, reached the limit before Voyager 2, which went south. Recent studies have shown that the interstellar magnetic field above the Sun could also be stronger than expected. This field interacts with the solar magnetic field at the boundary of the heliosphere, shaping the protective shield around our solar system. The collision zone above may become more turbulent or compressed as the solar system moves deeper into the magnetic folds of the local bubble's edge. This matters because it affects how many galactic cosmic rays penetrate into the inner solar system, especially from the galactic north. Even Earth-based observatories have played a role in mapping this boundary. Through the study of interstellar absorption lines in the spectra of distant stars, scientists can track how much gas and dust lies between us and those stars. By targeting stars in the galactic north, researchers can infer the depth and structure of the local bubble's roof. This approach has allowed astronomers to create 3D maps of the bubble's contours, showing that its upper boundary might be uneven and possibly eroded by interaction with neighboring superstructures. Supernovae don't just shape local space. They distribute elements like iron, oxygen, and silicon into the interstellar medium. The upper boundary of the local bubble may still carry traces of these ancient explosions, making it a laboratory for studying elemental enrichment and the recycling of stellar material. Even with all of our progress, this area is still not fully settled. One day, missions like the planned Interstellar Probe or future soft X-ray mapping missions might be able to go through or take pictures of this upper boundary in great detail. This would finally show us what the edge of our bubble really looks like. What's up there above the Sun? Not a smooth exit into the galaxy, but a transition zone with many layers, high pressure, and a lot of heat. If you can call it that, the remains of dead stars form an atmosphere that wraps around our solar system like a cosmic weather shield. Magnetic fields above the heliosphere. Most of the time, when we think of space, we picture a dark, empty place full of stars. There are forces in space, though, and magnetic fields are one of the least known of them. Above the heliosphere, the solar wind's protected bubble, there is an area where the Sun's impact starts to weaken, and the interstellar magnetic field takes over. It can't be seen or touched, but it's very important to know how the solar system connects to the rest of the world. The heliosphere is shaped by a constant tug-of-war. On one side is the solar wind, charged particles streaming from the Sun. On the other side is the interstellar medium, made of gas, dust, and magnetic fields that exist between stars. Where these forces meet, the solar wind slows down, becomes turbulent, and eventually halts at a region known as the heliopause. And it's just beyond this boundary, particularly above the Sun's north pole, that the external galactic magnetic field begins to assert its control. Voyager 1 made one of the most important discoveries in our knowledge of this area. When it left the heliosphere in 2012, it sent back data that no one expected. Scientists thought that when Voyager 1 crossed the heliopause, the direction of the magnetic field would change quickly. Instead, Voyager 1 found a more gradual change. The Sun's magnetic field didn't seem to have a clear edge. Instead, it seemed to slowly twist and mix with the field beyond in the galaxy. This suggested a much more complicated interaction zone, where magnetic lines don't just stop. They join, fold, and maybe even twist. The magnetic fields above the heliosphere act as both gatekeepers and highways. They influence how cosmic rays, high-energy particles from distant parts of the galaxy, enter our solar system. When those rays approach from above, the orientation of interstellar magnetic fields can deflect, filter, or even guide them toward the heliosphere's boundaries. During periods of low solar activity, when the solar magnetic field weakens, the interstellar magnetic field becomes more dominant, allowing greater cosmic ray penetration, especially from the galactic north. This isn't just theoretical. Instruments like IBEX, Interstellar Boundary Explorer, and Cassini have helped detect a faint ribbon of energetic neutral atoms encircling the sky, believed to be aligned with the direction of the local interstellar magnetic field. This ribbon provides a visual cue of how the heliosphere interacts with magnetic forces from above and beyond. It forms a kind of cosmic scar, evidence that the Sun is being wrapped, pressed, and sculpted by external fields. The shape of these fields is one of the riddles that scientists are still trying to solve. Like the lines around a bar magnet, are they smooth and even? Or are they mixed up because of the wind from supernovae in the past, the spinning of the galaxy, and stellar winds? Not only for astronomy, but also for space travel, the answer is very important. Particles can be sped up to almost the speed of light by magnetic fields, or they can get stuck in dangerous bands. They can also change how spaceships talk to each other, how much protection is needed, and how they can find their way far beyond Earth. Above the heliosphere, the magnetic field strength is estimated to be around 3-6 microgauss, much weaker than Earth's field, but still enough to shape large-scale cosmic structures. It's thought that our solar system may be entering a new magnetic region within the local interstellar cloud. This could compress or reshape the heliosphere in the coming thousands of years, possibly even altering the balance of protection that shields planets from cosmic radiation. And then there's the potential link to the North Galactic Spur, a massive arc of gas and magnetic activity that looms above the galactic plane. Some researchers believe the interstellar magnetic field above our solar system could be influenced or even partially aligned with this structure, creating a wider magnetic corridor through which particles, dust, and radiation flow. To learn more about this strange place, new trips are being planned. One of these is the Interstellar Mapping and Acceleration Probe (IMAP) project, which will take off in the late 2020s. Its job is to draw a picture of how particles speed up at the edge of the heliosphere and how the magnetic field between the stars affects that process. IMAP could help us figure out the real shape and direction of the fields above the Sun if it had more sensitive equipment. This would help us learn more about how we fit into the galaxy's magnetic structure. In the end, the magnetic fields above the heliosphere aren't just straight lines. They're living with movement and can change. They collect energy from space, make the shield around our solar system, and tell us about the past of our area of the galaxy. Interstellar dust concentrations above the ecliptic plane. The ecliptic plane, which is the flat line of planets in our solar system, is surrounded by cosmic dust, a layer of matter that we can't see but is always there. People often think of this dust as just background haze, but it has a big impact on what we can see, where our satellites can go, and how sunlight behaves on its way to Earth. We can see places where the amount of dust changes a lot when we look above the ecliptic. These areas offer new ways to observe the universe and new secrets. The ecliptic plane itself is formed by the orbital path of Earth and the other major planets. Most of the dust in our immediate vicinity lies along this flat plane, generated by collisions of asteroids and comets over billions of years. This is the source of zodiacal light, the faint triangular glow that appears just before sunrise or after sunset. But above the ecliptic, the concentration and behavior of dust begin to shift. At first glance, one might expect that dust density would simply decrease with distance from the ecliptic. And generally, that's true, especially for dust originating from solar system sources. But as you move further out, past the orbit of Neptune and beyond the Kuiper belt, the solar system's own dust thins out. What takes its place, especially above and below the ecliptic, is interstellar dust, tiny grains of carbon, silicates and ice drifting into our region of space from beyond the solar system. This dust doesn't just appear out of nowhere. There are magnetic fields and shock waves in the local interstellar medium, LISM, that shape it. As the Sun moves through this medium, it comes across areas of dust that are heavier or less thick. These particles aren't moving in a straight line with the Sun. It's a little off from straight above the equator of the Sun, which means that a lot of this cosmic matter comes into the solar system from the direction of the galactic center, which is north. More or less, a steady stream of strange dust falls from the sky. Spacecraft like Ulysses, Galileo, and Cassini have helped detect and analyze these particles. Ulysses, in particular, had a unique orbit that took it over the poles of the Sun, allowing it to detect incoming interstellar dust from above the ecliptic. What it found surprised scientists. The grains were larger and faster than expected, and their trajectories appeared aligned with the local interstellar magnetic field, hinting at large-scale order in what was once thought to be random cosmic debris. There are effects to this dust. It works with the heliosphere, charging particles as they come in and might change the shape of the edges of the solar wind. It also changes what can be seen from Earth. Dust between the stars acts as both a lens and a screen when we point binoculars above the plane of the galaxy. Some bands of light, mostly ultraviolet and visible light, are absorbed by it, but infrared light can pass through. Infrared light is very important for space satellites like Spitzer and James Webb because it lets them see through dusty areas and see what's beyond them. The distribution of dust above the ecliptic isn't uniform either. It's clumpy, with denser streams and voids depending on the Sun's local position in the LISM. Observations have shown that some of this dust may come from ancient supernova remnants, rich in heavy elements, and may even carry prebiotic compounds that have traveled across interstellar space for millions of years. Studying these grains could offer insights into the chemistry of other planetary systems and the origins of organic matter in our own. There are even traces of this interstellar dust embedded in Earth's atmosphere. During certain times of year, Earth passes through streams of these high-altitude particles, where they burn up and contribute to micrometeorite showers. Some survive the journey and have been found in polar ice cores and deep-sea sediments, tiny messengers from outside the solar system. From a mission planning perspective, understanding dust concentrations above the ecliptic is crucial. Spacecraft traveling on non-planar trajectories, like future interstellar probes or solar polar orbiters, must be designed to withstand impacts with these high-velocity grains. Even though they're microscopic, their speed, often tens of kilometers per second, gives them tremendous kinetic energy. Over time, these impacts can degrade instruments, damage surfaces, or affect navigational accuracy. In the future, projects like NASA's IMAP and the planned Interstellar probe will look into how dust comes into the solar system from above in more detail. These trips will help us improve our models of dust concentration, particle makeup, and electromagnetic alignment. This will give us a better idea of how stuff from the galaxy reacts with the layers that protect our star. The Great Attractor and large-scale cosmic motion overhead. Beyond the spiral arms of the Milky Way and the nearby clouds of gas and dust, very high above the solar system, there is a huge, powerful thing that can change the paths of galaxies. Even though we can't see it, we know it's there. It's called the Great Attractor. Why? Because all the galaxies in the local group, including our own Milky Way, are being pulled toward it very quickly. The interesting part is that this gravity pull comes from above the galactic plane, which changes the way our solar system moves through the universe in a subtle way. Discovered in the 1980s, the Great Attractor isn't a specific object, but a gravitational anomaly, a region of space where matter is unusually concentrated. Galaxies near this region are accelerating toward it at about 600 kilometers per second, and our galaxy is caught in the same flow. This collective drift is called peculiar velocity, and it refers to motion that deviates from the uniform expansion of the universe, which should be carrying everything outward. Therefore, what is there facing the Great Attractor? It is in the constellation Centaurus, in a part of the sky called the Zone of Avoidance that is very hard to see because of the Milky Way's disk and dust. It is hard to make direct readings in this area because it is close to the plane of our galaxy, but scientists can see through the dust with X-ray, infrared, and radio telescopes. What they see are groups of galaxies moving toward a dense core. One of the biggest gravity wells in our area of space is thought to be the Norma cluster, Abell 3627. But here's where it gets even more interesting for the solar system. The motion toward the Great Attractor is not perfectly aligned with the galactic center. It actually curves slightly upwards when measured against the solar system's position in the galactic disk. That means we are not only orbiting the center of the Milky Way, but also drifting in a trajectory that points above the galactic midplane toward this gravitational hotspot. This upward pull impacts our entire reference frame. The cosmic microwave background, CMB, the relic light from the Big Bang, appears slightly hotter in the direction we're moving and slightly cooler in the opposite direction. This effect, called CMB dipole anisotropy, was one of the first clues that our galaxy isn't just rotating, it's traveling towards something massive, and that something aligns closely with the direction of the Great Attractor. The story doesn't end there, though. More in-depth studies of how galaxies move have shown that the Great Attractor might be a part of a formation that is even bigger, the Shapley supercluster. This huge group of galaxies is farther away, but they are all moving in the same general direction. This suggests that the Great Attractor might not be the final goal, but rather a gravitational stepping stone on a cosmic river of matter. This has huge implications for our understanding of the cosmic flow. Galaxy clusters are not randomly scattered. They form filaments and walls around vast empty voids, like bubbles in a cosmic sponge. The flow toward the Great Attractor is part of this larger network, and our position within it means we're being subtly influenced by mass concentrations far beyond our visible horizon. These flows even affect how we chart the universe. When astronomers measure redshifts, how much the light from galaxies is stretched as the universe expands, they have to correct for our own motion. Because we're moving toward the Great Attractor, it skews our perception of galaxy positions, velocities, and distances, especially in the northern hemisphere sky, where this motion curves upward. Even so, the Great Attractor is still a secret, despite how powerful it is. We know it's there and what it's doing, but we're not sure why it's so thick or how it fits into the bigger picture. Some scientists think that behind the Milky Way, there may be secret dark matter halos, or even more massive clusters that can't be seen. These could be ready to be found with next-generation infrared and gravitational wave observatories. The Galactic Halo, diffuse matter above the Milky Way. Beyond the dense disk where most of our stars' gas and dust dwell, above the flat spiral arms of the Milky Way, there lies a huge ghostly stretch of matter that we can hardly see but has a huge gravitational pull on everything in our galaxy. This is the ring around the galaxy. It covers the Milky Way like a sphere that is almost invisible and goes far above and below the plane of the galaxy. And as the Sun moves around the galaxy, it moves inside this strange ring, just touching the bottom edge of a huge structure that no one really understands. The galactic halo can be divided into two components, the stellar halo and the dark matter halo. The stellar halo contains ancient stars and globular clusters, some of the oldest stellar populations known. These stars don't rotate with the rest of the galactic disk. Instead, they follow eccentric tilted orbits, some of which arc far above the plane of the galaxy. They provide crucial clues to the Milky Way's violent formation history, including mergers with smaller galaxies whose remnants were scattered across the halo. The dark matter ring is the second and much bigger part. This ring is thought to make up most of the Milky Way's mass, even though it doesn't give off light. It goes on for hundreds of thousands of light years in every direction, spreading out in a roughly circular pattern that changes the way stars move in the galaxy, even though we can't see or touch it. Based on how much mass we can see, the stars in the Milky Way should spin slower than they do. This difference only makes sense if the galaxy is held together by a huge, hidden ring. What lies above the solar system in this context is the upper region of the halo, filled with hot, diffuse plasma, sparse ancient stars, and the pervasive gravitational presence of dark matter. Unlike the busy, crowded disk, this region is quiet and tenuous, with particle densities far lower than even the best laboratory vacuums on Earth. And yet, it's everywhere, forming a cushion that holds the galaxy in its shape and likely preventing smaller satellite galaxies from escaping its pull. Astronomers have detected the hot gas halo, a component called the circumgalactic medium, CGM, by observing how it absorbs X-rays from distant quasars. These observations suggest that the Milky Way is surrounded by a reservoir of superheated gas at temperatures ranging from 1 to 10 million degrees Kelvin. This gas glows faintly in X-rays, and while nearly invisible in other wavelengths, it's believed to hold more mass than all the stars in the Milky Way combined. Some of the densest concentrations of this plasma are found above the galactic plane. Studying this region is not easy. The halo doesn't produce sharp images. It must be inferred by its effects through the scattering of light, the bending of radio waves, and the absorption lines in background sources. Missions like Rosat, Chandra, and XMM Newton have provided valuable data, but new missions are on the horizon, like XRISM and Athena, which will offer even more precise measurements of this hot halo. The Fermy Bubbles, two enormous lobes of gamma-ray radiation that rise above and below the galactic center, are also embedded within the halo. These bubbles extend tens of thousands of light years and may have been formed by ancient outbursts from the Milky Way's central supermassive black hole. They provide direct evidence that the halo is not a static structure. It can be shaped, shocked, and stirred by extreme energy releases from within the galaxy. And even though the halo looks huge and out of reach, the solar system is connected to it. We are part of it. As the Sun moves around the center of the galaxy, it goes through gentle vertical cycles, moving slightly above and below the plane of the galaxy every 30-35 million years. This means that as time goes on, our solar system moves through different, heavier parts of the halo. These changes could affect the space between the stars and affect us here on Earth. It's possible that going through larger groups of dark matter or halo gas could have small but interesting effects on the solar system. Some experts have even thought that these vertical moves through the halo might be connected to seasonal changes in the number of comet impacts or the Earth's temperature. This hasn't been proven yet, but it shows how little we really know about the things around our home galaxy. Fermi Bubbles, massive gamma-ray structures above our core. Above and below the center of the Milky Way are two huge bands of high-energy radiation that can't be explained in any easy way. The Fermi Bubbles are features found by NASA's Fermi Gamma-Ray Space Telescope in 2010. They are about 25,000 light-years above and below the galactic plane. That's almost how far Earth is from the galaxy's heart. They are huge, perfect, and full of energy. These aren't just parts of the galaxy's heart. What's above us includes them a lot. Gamma rays, which are the most powerful type of light, make up the Fermi Bubbles. Gamma rays are not like X-rays or infrared light. They are created by the universe's most extreme events, like black hole jets, supernovae, or particle collisions at relativistic speeds. The bubbles stand out because of how big they are and how sharp their tips are. They don't just slip away into the background. They look like they were cut, like bright scars in the galaxy's halo. These bubbles rise far above the galactic disk, piercing the galactic halo we discussed earlier. Observations suggest they are filled with hot plasma, high-energy particles, and magnetic fields. They may be expanding at speeds of up to 1,000 kilometers per second, yet no current supernova or starburst region inside the Milky Way seems powerful enough to have created them recently. That leads scientists to a more dramatic hypothesis. The Fermi Bubbles are likely the aftershock of an ancient outburst from the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. There was more noise in Sagittarius A star in the past, this idea says. It may have been an active galactic nucleus, AGN phase, millions of years ago, where it briefly ate gas around it and sent strong jets of particles straight up and down from the galactic plane. These jets would have sped through the space between the stars, sending huge shockwaves that blew up the Fermi Bubbles. This heated the gas and made gamma rays when particles hit each other and moved faster along magnetic fields. Other theories suggest a starburst event. A rapid period of star formation near the galactic center might have driven powerful winds outward, pushing energetic particles in both directions. Either way, the result is the same. Two giant energy lobes towering above and below our galaxy, remnants of a violent ancient event whose echoes are still visible in gamma rays. The structure of the Fermi Bubbles is multi-layered. Inside, they may contain X-ray emissions, observed by instruments like ROSAT and Erosita, and they appear to be bordered by shocks or pressure fronts. These boundaries, mapped in multiple wavelengths, reveal how the bubbles interact with the surrounding halo gas, possibly compressing it and changing its temperature and density. In some regions, the bubbles overlap with the North Galactic Spur, further complicating the map of what's really up there. The fact that the Fermi Bubbles are not steady is very interesting. Based on the data we have, they may be changing over time. Depending on the balance of internal pressure and the resistance of the interstellar medium around them, they may either grow or fade. Because they are symmetrical, whatever made them was also well-centered, which is another hint that the black hole is where they came from. Astronomers are now studying the polar regions of the Milky Way, above and below the galactic core, with increasing interest. If structures like the Fermi Bubbles exist in our galaxy, it raises the possibility that other spiral galaxies might host similar features hidden in plain sight. In fact, radio lobes observed in galaxies like Centaurus A resemble these bubbles, suggesting this may be a common but underappreciated phase in galactic evolution. From Earth, we don't see the Fermi Bubbles with our eyes, but gamma-ray telescopes have mapped them clearly, and they occupy a huge portion of the sky. If gamma rays were visible to us, The night sky would be dominated not by constellations, but by two vast glowing towers of energy reaching high above and below the Milky Way's glowing band. Dark matter filaments passing over the solar system. High above the ecliptic plane, where our telescopes can't see directly, rivers of gravity move through the universe without making a sound. These are dark matter strands, which are huge structures that look like webs and are thought to connect everything in the universe. Even though we can't see them, they affect how galaxies, groups, and maybe even our own solar system move. Modern astronomical models say that these filaments aren't just on very large sizes in the universe. They may also go right over and around our solar system, weaving through the Milky Way like ghostly scaffolding. Dark matter itself is still a mystery. It doesn't emit, reflect, or absorb light, which means we can't observe it directly. But we know it's there. Its gravitational fingerprints are everywhere, most notably in the way galaxies spin. Without dark matter, stars on the outer edges of galaxies would fly off into space. And beyond galaxies, simulations of the universe's evolution show that dark matter forms an enormous cosmic web, with filaments connecting dense nodes where galaxies form. These dark matter filaments are hundreds of millions of light-years long, but they're not smooth lines, they have structure. They're denser near massive clusters, thinner in voids, and may intersect with smaller filaments inside galaxies themselves. Our Milky Way is not exempt. Though we're located within a spiral galaxy, that galaxy is embedded within a local dark matter environment, possibly with smaller subfilaments crisscrossing our position in the galactic disk and extending above and below it. Since we can't see them, how do we know they're real? The answer lies in gravitational lensing, which is the way that light from galaxies far away bends as it passes close to big objects. Astronomers can figure out where mass is located, even when that mass can't be seen by looking at how large-scale sky scans are distorted. The maps always show structures that look like filaments connecting galaxy groups, like spiderweb lines going through empty space. Some simulations suggest that our solar system may, at times, pass through or near these filaments, especially the dark matter subhalos that move independently within the Milky Way's larger dark matter halo. These subhalos could be dense enough to create gravitational perturbations, detectable through precision measurements of planetary orbits, or even through transient gravitational lensing effects. While we haven't yet directly confirmed one of these local filaments, ongoing research is closing in. Missions like ESA's Gaia are helping by tracking the motion of over 1 billion stars in our galaxy. Subtle wobbles or drifts in stellar streams may indicate the passage of dark matter clumps, especially those moving vertically through the galactic disk. If a dark matter filament were passing above the solar system, we might detect it not through light, but through the motions of stars and gas being subtly pulled by its gravitational influence. More and more people are also wondering if dark matter strands could change the way cosmic rays travel. Denser areas of dark matter above or below the galaxy plane could slightly change these particles' paths or energies because they move along magnetic fields and are affected by gravity wells. Some experts think that these effects could be used as secondary proof of the shape and movement of dark matter filaments around us. Could these filaments pose a threat? Most likely, no. They are incredibly diffuse. Even in the densest regions, they contain only a few particles per cubic meter. But their gravitational impact is enormous, especially on large-scale structures like star clusters, stellar streams, and the gas clouds that form new stars. Over millions of years, dark matter filaments may influence how material clumps, how orbits shift, and even how frequently comet clouds like the Oort cloud get perturbed, sending icy bodies inward. In the future, projects like LISA, Laser Interferometer Space Antenna, and CMBS-4 will try to find weak signs, such as gravitational waves or distortions in the cosmic microwave background, that might help us learn more about dark matter structures and how they behave. If it turns out to be true, we might be looking up at rivers of light that are moving quietly across the galaxy and changing how it evolves without ever shining a light on us. Rogue planets entering from galactic north. Rogue planets are the most lonely tourists in the world. They float above the solar system in the dark spaces between stars. These are planets that used to circle a star but no longer do. Some were thrown from their home systems during strong gravity collisions. Some may have formed while they were not connected to a sun at all. A lot of them float through the galactic disk, but some fall in from above, joining the Milky Way's plane from the direction of galactic north. They might even pass close to our solar system without being seen. Astronomers have detected a growing number of them using microlensing, where the gravity of a massive object briefly magnifies the light from a more distant star as it passes in front. This method has revealed planets not tied to any stellar system, with masses ranging from Earth-sized to several times that of Jupiter. Some studies suggest there may be billions of these wanderers drifting through the galaxy, possibly even outnumbering stars. So how do they get above the galactic plane in the first place? The Milky Way isn't flat. It's a dynamic, vibrating system. When galaxies collide, merge, or interact, gravitational disruptions can send stars and planets flying off-plane. Some rogue planets likely came from disrupted dwarf galaxies or star clusters that passed through the Milky Way at an angle, leaving behind trails of scattered debris, including planets. Others may have been ejected from binary star systems or multi-planet systems by chaotic orbital dynamics, sent arcing high into the galactic halo before looping back down toward the disk. If a rogue planet enters from the galactic north, it approaches the solar system from above the ecliptic. That makes detection even more difficult, since most of our telescopes are optimized to scan along the galactic plane or within the solar system's orbital disk. These vertical intruders are stealthy, cold, dark, and invisible in normal light. Without a parent star, they emit no glow. Their only signature might be the faint warmth of internal radiation, detectable in infrared wavelengths with highly sensitive instruments like JWST or the upcoming Nancy Grace Roman Space Telescope. Could one get close to us? Based on numbers, the chances are not good. There are a lot of different worlds in space, but the solar system is still a very small goal. But it's not impossible. Some models say that once every few million years, a strange object might come within a few light years of the Sun. This could upset the Oort cloud and cause a wave of comets to come closer. It wouldn't have to be a direct hit for chaos to happen. Just a close pass could send waves through the outer solar system like a stone touching the edge of a pond. There's even speculation that our solar system may have encountered rogue planets in the past. One hypothesis for the hypothetical Planet 9 is that it could actually be a captured rogue, snatched into a long elliptical orbit by the Sun's gravity during a close encounter. While evidence remains inconclusive, it's not impossible. The gravitational signatures of unknown objects in the outer solar system leave open the possibility that something came in from above and never fully left. The arrival of rogue planets from galactic north also holds clues about the vertical dynamics of the galaxy. They can be used as tracers, objects that reveal the shape and behavior of the Milky Way's gravitational field. By studying their motion, astronomers can refine models of the galactic halo, disk wobble, and the influence of dark matter. These cold planets, though quiet and unlit, could help map the invisible scaffolding of our galaxy. In the future, especially studies that look at big parts of the sky at different wavelengths, these space travelers may finally be found more consistently. Space-based microlensing projects, missions like Euclid and the Vera Rubin Observatory, will look for the faintest signs of these secret masses moving quietly across the stars, preferably from places that aren't seen as much, like galactic north. The North Celestial Pole and its role in sky alignment. The North Celestial Pole is a spot in the sky that has been used as a guide by sailors, scientists, and stargazers for hundreds of years. It is high above the Earth and is surrounded by the quiet northern stars. The point in the sky that Earth's rotational axis points to is not a real thing, but a reference point. From where we are on Earth, it looks like the point around which the whole northern sky revolves. But it's important for a lot more than just direction. It is very important for how we position sensors, measure motion, and figure out where we are in space in terms of our galaxy. The North Celestial Pole is famously marked by Polaris, the North Star. It sits almost directly above Earth's North Pole, making it a near-perfect anchor for orientation. If you were to stand at the Earth's geographic North Pole, Polaris would shine directly overhead. But this alignment is only temporary. Earth's axis precesses a slow 26,000-year wobble like a spinning top. Over time, this wobble shifts the North Celestial Pole in a slow circle through the sky. Thousands of years ago, Thuban in the constellation Draco was the North Star. Thousands of years from now, it will be Vega. This motion doesn't just affect our calendars and navigation systems. It affects how we align telescopes, how we track satellites, and how we define our coordinate systems in astronomy. For Earth-based observations, the North Celestial Pole is the hinge around which the night sky spins. Long exposure photographs show this beautifully. Stars streak in perfect circles around Polaris. But this pole is also our visual anchor for understanding sky motion, and it provides a vital constant when studying celestial mechanics. The Earth's axis points toward the North Celestial Pole, but in a larger context, the solar system itself has its own north, the solar North Pole, which points in a different direction entirely due to the tilt of Earth's orbit relative to the solar equator. And the Milky Way has yet another reference frame, defined by the galactic North Pole, which sits in the constellation Coma Berenices, far from Polaris. These poles are not aligned, which means that up from Earth is not the same as up for the solar system or the galaxy. When mapping deep space, this mismatch is very important. There are three types of coordinate systems that astronomers use to look for galaxies, nebulae, and cosmic microwave background radiation. These are equatorial coordinates, which are based on how the Earth spins, ecliptic coordinates, which are based on the path of the Sun, and galactic coordinates, which are based on how the Milky Way is organized. The North Celestial Pole is the center of this change. It's where Earth-based sky direction starts and ends. Because Polaris is so stable, remaining nearly motionless in the sky, it serves as a key alignment point for telescopes, especially those with tracking mounts. It's also used for satellite calibration, antenna positioning, and long-distance communication alignment. When spacecraft leave Earth and venture into solar or interstellar space, mission controllers often reference both the celestial pole and galactic reference frames to track their trajectory and orientation. The North Celestial Pole also helps track Earth's axial precession and nutation, the subtle wobbling of the axis over time due to gravitational forces from the Moon and Sun. These movements can be measured with extreme precision by tracking how the pole shifts relative to background stars. The data feeds into everything from space mission timing to climate models. As Earth's axis shifts and the North Celestial Pole slowly draws a circle in the sky, it changes what part of the universe we're naturally aligned with. Over millennia, this affects what parts of the galaxy are most visible from our location, which stars dominate our sky, and which constellations align with the seasons. In a sense, it changes how humanity sees the cosmos, generation by generation. Know this: when you look up at Polaris, you're not just seeing a star. You're pointing straight down the Earth's axis of spin toward a place that tells us where we are in the universe. And after that, a whole sky that changes slowly, consistently, and beautifully, going around a pole that seems to last forever but is always moving. Plasma clouds and stellar winds from above. Above the solar system's ecliptic plane, which is mostly calm, things get wild, chaotic, and electric. There is a world of plasma clouds and star winds here, away from the gravitational dance of planets' orbits. These are hot, charged streams of particles moving through space at very high speeds. These unseen tides, which mostly come from stars close by and far away, shape the edge of our solar system, affect the paths of satellites, and may even move the very edge of our protective heliosphere. Let's start with what we mean by plasma. In space, plasma isn't some exotic substance. It's the most common state of matter. It's a hot, ionized gas composed of free electrons and nuclei, and it's incredibly responsive to magnetic fields. Above the solar system, this plasma comes from several sources: the Sun, nearby stars, past supernovae, and turbulent regions in the local interstellar medium, LISM. Once released, these particles don't just float aimlessly. They ride along magnetic field lines, sometimes stretching vast distances across the galaxy. The most direct plasma influence on our solar system is the solar wind, a continuous outflow of particles emitted from the Sun. While this wind expands in all directions, the polar solar wind, coming from the Sun's north and south poles, behaves differently. It's faster, more stable, and less dense than the wind from the equatorial regions. During periods of solar minimum, the polar wind dominates, flowing outward in relatively straight streams that travel far into space, extending well above the plane of the planets. These polar winds play a critical role in shaping the heliosphere, the bubble of solar influence that surrounds the entire solar system. Above the solar system, particularly toward the galactic north, the heliosphere is compressed or extended depending on the opposing pressure of external plasma and interstellar winds. Instruments aboard Ulysses, which flew over the Sun's poles, revealed that these fast winds create coronal holes, regions of lower density on the Sun's surface that allow charged particles to escape more easily into space. Nearby stars, especially massive or young ones, also generate powerful stellar winds, sometimes thousands of times stronger than the Sun's. These winds can send shock waves through the local interstellar medium, colliding with each other and forming complex plasma clouds that move slowly through the galaxy. As our solar system drifts through the Milky Way, it occasionally encounters these pockets of ionized gas. The Sun is currently moving through the local interstellar cloud, LIC, which is one of these structures. This cloud is made up of hot, low-density plasma and cold neutral gas. It is thought to have been formed by several supernovae from close OB groups. The line where the heliosphere hits this cloud is always moving because it depends on how strong and which way the plasma and magnetic fields are coming from. Above the solar system, this contact can cause magnetic chaos and change the way that cosmic rays and particles from other stars enter the solar system. Instruments like IBEX, Interstellar Boundary Explorer, and Voyager 1 and 2 have helped detect the effects of this interface. IBEX, for example, observed a ribbon of energetic neutral atoms, ENAs, thought to form where the solar wind collides with the plasma of the LISM, particularly along directions perpendicular to the interstellar magnetic field, which includes regions above and below the solar equator. The fact that these plasma flows can be fragile and changeable is very interesting. There aren't as many things to use as reference points above the solar system, so plasma clouds may be hiding density groups, pressure waves, or even remnants of supernova that happened a long time ago. These disturbances move through the space between the stars like waves that can't be seen. Sometimes they crash into the heliosphere and change its size or shape. There's also the possibility of plasma instabilities, regions where electric and magnetic fields twist and amplify, potentially generating high-energy particle bursts or distorting incoming signals. These phenomena make above-the-plane space a challenge for both communications and navigation. Any future spacecraft venturing out of the solar system in the northern galactic direction will have to contend with this unpredictable plasma weather. And yet, studying these clouds could reveal much about the composition and behavior of the interstellar medium. Missions like the upcoming IMAP spacecraft will map how particles are exchanged at the solar system's edge, offering better insight into what exactly flows in from above. The Laniakea supercluster's structure above our zone. We usually think of things close to home when we talk about what's above the solar system, like solar wind, rogue planets, and dust clouds. But if you zoom out enough, above means something much bigger. The solar system is not only a part of the Milky Way, it is also a part of the Laniakea supercluster, which is a very large object in space. This supercluster is made up of thousands of galaxies, including our own. that are all moving toward an unknown center point. It spans more than 500 million light-years. A big part of that structure goes above the plane of our galaxy and out into the great sky in the north. The name Laniakea means immense heaven in Hawaiian, and it fits. This isn't just a cluster of galaxies, it's a gravitational basin, a sprawling structure where galactic flows converge. At the heart of Laniakea lies the Great Attractor, the gravitational anomaly we discussed earlier, which pulls galaxies inward like a whirlpool. The Milky Way, along with the Andromeda Galaxy and hundreds of other systems in the Virgo cluster, is just one stream in this grand motion. The discovery of Laniakea in 2014 changed how we map the universe. Previously, galaxy clusters and superclusters were defined mostly by appearance, but Laniakea was mapped using peculiar velocity data, the measured motion of galaxies relative to the overall expansion of the universe. By plotting how galaxies move through space, astronomers were able to reveal gravitational rivers, showing that many galaxies we thought were independent are actually falling together into one enormous structure. What does this have to do with the sky? From where the Sun is in the Milky Way, most of Laniakea's mass is above the plane of the galaxy, toward constellations like Virgo, Centaurus, and Hydra. In terms of our galaxy's coordinates, this means we're looking upward into the densest parts of our home. The sky in the northern hemisphere shows a denser, more complex cosmic web when we look at large-scale structure studies. Many of the largest galaxy flows point in this direction. This vertical alignment has practical effects. Observatories studying large-scale cosmic structure, such as the Sloan Digital Sky Survey, SDSS, the 2-Micron All-Sky Survey, 2MASS, and the Cosmic Flows Project, often scan northern skies because of the Laniakea density in that direction. The galactic plane, cluttered with stars and dust, obscures much of the southern perspective. But above the plane, through windows like the Northern Galactic Cap, we get clearer access to galaxies and cosmic voids beyond. Within this upper structure, astronomers have mapped various cosmic filaments, thread-like formations where galaxies cluster together. These filaments channel matter towards central hubs, like the Great Attractor or the Shapley supercluster, all nested within Laniakea's gravitational domain. The Milky Way itself appears to be traveling along one such filament, rising into the northern extent of the supercluster, part of a galactic flow climbing through the structure's vertical spine. What's more, cosmic microwave background, CMB data, particularly the dipole anisotropy, confirms that the solar system is moving in this upward direction. The slight hotter and cooler regions of the CMB tell us that we're drifting toward a large mass concentration, one that aligns with Laniakea's northern axis. It's not just a static map, it's a directional reality. The solar system is literally climbing upward through this part of the cosmic web. We're still only starting to understand this huge structure though. Laniakea is marked by gravitational motion, not just visible light, so it takes a lot of powerful telescopes and complicated modeling to make a picture of it. More detailed information will be revealed by upcoming projects like Euclid, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope. For example, these projects will help show how galaxy groups move in relation to dark matter, and how these vertical flows change over billions of years. There's even the philosophical implication, not in a metaphysical sense, but in the practical one. We are part of a structure far larger than a galaxy, and our motion is not random. We are being pulled upward and inward along invisible gravitational pathways toward a destination that exists far above our current understanding. The observable universe's boundary in the northern sky. The edge of the visible universe is one of the most important boundaries in all of science. It is above the solar system, past the dusty disk of our galaxy, and past the scatter of nearby stars. The world may be endless, but the part that we can see, the part where light has had time to reach us since the Big Bang, is limited. And when we look up into the deep northern sky above the solar system, we are looking right at the edge of what we can see. The observable universe stretches roughly 46.5 billion light-years in every direction, not because the universe is that young, but because space itself is expanding. This means the most distant galaxies we can see are not just far, they're receding, carried away by the stretching of space-time. This expansion creates a natural horizon, beyond which light simply hasn't had time to reach us. It's not a wall, but a limit defined by time and distance, wrapped around us like an invisible shell. From Earth's vantage point, astronomers use galactic coordinates to define directions like up and down. Looking toward galactic north in the direction of the North Galactic Pole gives us one of the cleanest windows out of the galaxy. Why? Because there's less interstellar dust and fewer bright foreground stars in that region. It's like looking through a clear patch in a crowded forest. You can see deeper, farther, and more clearly. The Hubble Ultra Deep Field, the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey have all pointed their telescopes towards the northern part of the sky to keep galaxy noise to a minimum. The number of galaxies they found was amazing. Many of them had only been made a few 100 million years after the Big Bang. Some of them look like weak spots of light because the expansion of the universe has sped up their photons to very high redshifts. In this direction, above the solar system, we've observed some of the most ancient light ever recorded. One example is the detection of quasars, extremely bright and active galactic cores powered by supermassive black holes. Some of these quasars in the northern sky have redshifts greater than Z equals sign 7. Meaning the light we see from them began its journey over 13 billion years ago, when the universe was still in its infancy. That light has traveled across expanding space, passed through intergalactic gas, dodged cosmic dust, and finally reached us, falling into our detectors from high above the plane of our galaxy. We also look in this direction to observe the cosmic microwave background, CMB, the afterglow of the Big Bang itself. Although the CMB bathes the universe uniformly, some regions, particularly those above the galactic plane, provide clearer, less contaminated measurements. Missions like COBE, WMAP, and Planck all focused on the northern sky to study tiny fluctuations in this ancient light. These fluctuations reveal density differences in the early universe, which later grew into galaxies, clusters, and cosmic structures we see today. But you can find more than just light. Future 21cm scans and upcoming telescopes like the James Webb Space Telescope, JWST, will look at this upper limit in infrared and radio wavelengths, finding the faintest signs from the time when the first stars were born. With these findings, a 3D picture of the early universe will be made, starting high above the solar system and going out to the edge of what can be seen in the universe. It's worth noting that the boundary we see above us today is not the same forever. Because light takes time to travel, the observable universe is always growing. Every second, more of the universe becomes visible, not because we're moving, but because light from farther distances is finally arriving. And much of that newly visible space first appears along clear sight lines, like those found in the galactic north. The northern sky is also useful for space telescopes in positions like Lagrange Point 2, L2, which is where the JWST and the soon-to-be-built Nancy Grace Roman Space Telescope will work. These telescopes use the clear, unbroken northern field of view to do long-term deep-field studies, which are very important for discovering new things about the universe. Redshifted galaxies visible above the Milky Way disk. There is a quieter part of the sky above the thick, bright band of the Milky Way. It's a dark painting that doesn't have many stars or cosmic dust on it. Astronomers can find redshifted galaxies, which are very far away objects whose light has been stretched by the expansion of the universe, by pointing their telescopes up into this cleaner part of the sky, especially in the direction of the North Galactic Pole. This is one of the most powerful tools in the study of the universe. When you look up above the circle of the Milky Way, you can see farther into space and time. The galaxy plane of the Milky Way is packed full of stars, gas, and dust. Even though it's beautiful, this direction is terrible for seeing galaxies far away because all that matter blocks light. These places are known as high extinction zones by astronomers because light from behind the galaxy disk is either swallowed or spread out in these areas. But the amount of dust and stars that get in the way drops greatly when you look above the galactic plane, especially toward the northern galactic cap. This area is called a cosmic window because it is a rare, clear spot that lets us do deep scans of the galaxy. This area was used by the Sloan Digital Sky Survey, SDSS, as one of the first big projects. It looked at a huge part of the northern sky and made a 3D map of the universe with over 1 million galaxies that is one of the most thorough ever made. A lot of these galaxies have big redshifts, which means that their light is stretched toward longer wavelengths because the universe is expanding. When you look at redshift, a galaxy is farther away and earlier in time. Galaxies observed above the Milky Way's disk often have redshifts of z equal sign 0.5 to 2, corresponding to distances of several billion light-years. But deep field surveys like the Hubble Ultra Deep Field and more recent JWST observations have pushed this boundary even farther, detecting galaxies with redshifts of z equal sign 10 and beyond, meaning the light from those galaxies began its journey just a few 100 million years after the Big Bang. That light is only visible today because it's been redshifted into the infrared part of the spectrum, a shift caused not by the motion of galaxies through space, but by the expansion of space itself. This redshift phenomenon isn't just a curiosity, it's a cosmic ruler. By measuring how much a galaxy's light has stretched, astronomers can calculate how long it has been traveling, how far away the galaxy is now, and what the universe looked like at that moment in time. And thanks to the clarity of the northern sky above the Milky Way's disk, we can apply this ruler with unprecedented precision. These distant galaxies are often faint, so faint they're invisible to the human eye and even to many optical telescopes. That's why instruments like the James Webb Space Telescope, JWST, are designed to operate in the infrared, where these ancient light signatures have landed after their journey across billions of light years. Observing above the galactic plane avoids interference from the Milky Way's own dust, which strongly absorbs and re-emits infrared light, making these zones ideal for deep cosmological exploration. What astronomers are finding in this direction is nothing short of revolutionary. Some redshifted galaxies are small and chaotic, possibly still in the process of forming. Others appear surprisingly mature, with disks, bulges, and even early spiral structures, raising questions about how quickly galaxies could form in the early universe. Many of these discoveries challenge existing models of cosmic evolution, and they're all being made in the clean corridors above the Milky Way. The redshift ranges of even closer galaxies in the northern galactic cap are very interesting. These studies show that the universe is made up of voids, filaments, and walls. On a big scale, galaxies are grouped together in threads and sheets, with large empty spaces between them. Researchers can figure out how matter is spread on a cosmic scale, and how gravity has shaped the universe's skeleton over billions of years by mapping these redshifts. There's also a technological bonus to looking above the galactic disk: less noise. Space telescopes operating in the radio, microwave, and infrared bands suffer less interference from galactic synchrotron radiation, free emission, and thermal noise in this direction. That means deeper, cleaner data with fewer distortions, better signal-to-noise ratios, and higher confidence in redshift measurements. We will keep collecting redshift data from the sky as our tools get better and as AI-driven data analysis gets better. These galaxies that have been turned red are more than just dots in the distance. There is a frozen moment from the past in each of them, which could help us figure out how galaxies, stars, and maybe even life began. The Galactic South Pole, charting the other direction. The galactic North Pole leads us to brighter stars, better data, and older galaxies. The galactic South Pole is like the North Pole, but it has its own unique view of how the universe is put together. This area is in the constellation Sculptor and is 90 degrees below the galactic plane. It is the opposite pole in the galactic coordinate system. Even though it isn't as well known or studied as the galactic North Pole, the galactic South Pole is just as important for tracking the universe, looking at galactic symmetry and seeing how our Milky Way is shaped from above. Earth is positioned so that the galactic South Pole can mostly be seen from the southern hemisphere. It is in an area of the sky that, like the North, doesn't have many stars and cosmic dust in the center. This makes it a great time to look at objects outside of our galaxy, like galaxies, clusters, and the space between galaxies. Many of the first attempts to make 3D models of how galaxies are spread out, like those from the 2DF Galaxy Redshift survey, focused on this area because it has low visual extinction. The South Pole provides one of the cleanest cross-sectional views of the Milky Way's disk-to-halo transition. Observing in this direction allows astronomers to analyze the vertical structure of the galaxy, how stars, gas, and dark matter extend above and below the midplane. By comparing data from both poles, scientists can test whether the Milky Way's halo is truly spherical or subtly lopsided. Initial results suggest it's not perfectly symmetrical, with more substructures and possible remnants of galactic mergers showing up in the southern field. Calibration of all sky scans is another important job that the galactic South Pole does. Polar areas are often used by space telescopes like Galex, Spitzer, Chandra, and Planck to set baselines for signs from the cosmic background. These places don't have a lot of foreground noise, which makes them good for blocking out galaxy interference when studying the cosmic microwave background, CMB, or extragalactic X-ray emissions. Looking southward also opens a window to dwarf satellite galaxies of the Milky Way, including the Sculptor Dwarf Galaxy and the Fornax Dwarf Galaxy, both of which are located near the galactic South Pole. These small galaxies are critical for understanding dark matter, galaxy formation, and the hierarchical structure of the universe. Observations of their motion and composition help refine models of how the Milky Way grew through mergers and accretion. This region also contains portions of the South Galactic Cap, a high-latitude region frequently targeted by deep surveys. Just like its northern counterpart, the South Galactic Cap offers a relatively unobstructed path to observe large-scale cosmic structures like filaments and voids. In fact, when combining northern and southern sky surveys, astronomers can build all-sky maps of galaxy distribution necessary for truly 3D models of the universe. The galactic South Pole also features prominently in gravitational wave astronomy. Projects like LIGO and Virgo, and future space-based observatories like LISA, rely on full-sky coverage to triangulate the sources of gravitational waves. Polar regions, north and south, offer consistent visibility windows for long-duration scans, making them crucial for pinpointing merger events, black hole collisions, and neutron star impacts. Then there's the magnetic field component. The Milky Way's large-scale magnetic field runs roughly along the spiral arms, but field lines also loop vertically into the galactic halo. The southern pole, like the northern, gives astronomers a perspective on the vertical magnetic topology, helping to map the galactic dynamo that influences cosmic ray propagation, plasma flows, and synchrotron emissions. These observations are essential for creating accurate foreground models when studying deep cosmic radiation. It's important to note that the galactic South Pole is also used as a control area for scans and models of the sky. Scientists need areas of the sky with little noise to model things like dark matter abundance, baryon acoustic oscillations, or high redshift galaxy clusters. One such area is right below our galactic plane. It helps make sure that readings made in areas of the sky with more dust, people, or activity are not skewed in any way. So while the northern sky may get the headlines for ultra-deep fields and cosmic microwave imaging, the south is no less important. It offers balance, calibration, and an alternate perspective. It lets us peer into quieter parts of the universe and reflect on the symmetry or asymmetry of the galaxy we call home. Objects and currents beneath the ecliptic plane. A neat, flat disk with planets, moons, and comets all rotating in the same plane is how most of us picture the solar system. The path that Earth takes around the Sun makes that line, which we call the ecliptic. The universe, on the other hand, doesn't care about balance like we do. There is a much more complicated and little-studied area below this thin layer of order. It is full of rogue objects, old junk, and gravity currents that go around the solar system in strange ways. There is a secret world below the ecliptic. Asteroids and comets are the most well-known objects that live in this area. Most of them stay close to the ecliptic, but some, mostly those from the Oort cloud or with very steep paths, come in from above or below. Halley's Comet, for example, goes around the Sun in a backwards, tilted orbit that goes below the ecliptic and then quickly goes around again. Other things, like the dark icy centaurs and Damocloids that come from the outer solar system, often follow similar tilted paths that cut below the ecliptic like cosmic undercurrents. In fact, many long-period comets, originating from the distant reaches of the solar system, enter on near-random trajectories. When viewed from the side, these orbits form steep arcs, diving in from the deep south of the solar system and racing upward past the Sun. These comets are often only visible for short windows, but their paths provide clues to the gravitational forces at play far beyond the known planets. Beyond the Kuiper belt, the scattered disk extends in a thick halo of icy bodies, many of which lie significantly below the solar plane. Some theories suggest that Planet 9, the hypothetical massive planet proposed to exist in the far solar system, may be shepherding objects into highly inclined orbits, creating a population of detached trans-Neptunian objects with strange alignments. Several of these bodies approach the Sun from below the ecliptic, implying a gravitational disturbance lurking in the southern reaches of the system. Gravitational dynamics alone don't account for all that's beneath us. The solar system's motion through the galaxy creates a gravitational wake, what some call a bow wave, as it travels through the interstellar medium. This motion is not perfectly aligned with the ecliptic. Instead, we're traveling slightly angled upward in galactic terms, which means material from below the plane may be more susceptible to being swept inward by gravitational currents and interactions with the local interstellar cloud. Then there's the role of interplanetary magnetic fields and solar wind. The Sun's rotating magnetic field creates the heliospheric current sheet, a wavy, spiraling sheet of charged particles that undulates above and below the ecliptic plane. This sheet acts like a warped electrical blanket surrounding the Sun, and it can extend billions of kilometers outward. Beneath the ecliptic, the current sheet folds like a curtain, carrying solar particles and magnetic fields deep into space. These magnetic ripples can steer cosmic rays and trap interstellar particles in regions far from the visible solar disk. Several probes have looked into this area. Even though Ulysses was sent to study the solar poles, it also helped us learn how plasma moves and magnetic fields behave at high angles, which is not in a straight line. Voyager 2 went just below the ecliptic as it left the heliosphere. This gave scientists information about energetic particle streams, shocks, and the southern edge of the Sun's impact. It saw inequalities, which means that the space below the solar system might be organized differently than the space above it. Even small bodies closer to home hint at unseen structure below, near-Earth objects, NEOs, with inclined orbits such as 3,200 Phaethon, cross beneath the ecliptic in their long ellipses. These bodies can be difficult to detect with ground-based telescopes that scan mainly within the ecliptic band, meaning there could be numerous under-ecliptic objects we've simply missed. Observations of the zodiacal cloud, the diffuse disk of dust particles left over from asteroid collisions and comet outgassing, show that it has a thick vertical structure. Infrared studies have revealed a halo of dust both above and below the ecliptic, spreading out from the Sun in all directions. The dust below the plane scatters sunlight and re-emits it as infrared radiation, contributing to a faint but measurable glow. Missions like IRIS and WISE have mapped this emission, giving us clues about the dust's origin and motion. That being said, what is below the ecliptic? a complex web of strange orbital patterns, gravity flows, and electric currents. It's not an exact copy of the room above. Comets rise like ghosts in this area, where planets that can't be seen may hide, and where solar and galactic forces stretch space in ways that we're only just starting to understand. The underside of the Oort cloud, the farthest solar remnants. The Oort cloud is a huge spherical shell of icy debris that wraps around the solar system like a cosmic cage. It is far beyond the outer planets, past the Kuiper belt and the scattered disk. It is the farthest point that the Sun's gravity can reach, and it may be home to trillions of frozen items that were around when the solar system was first formed. But what's below it? What's on the bottom of this very old shell, which is right below the ecliptic and plunges into the farthest southern edge of space? The Oort cloud is thought to extend from about 2,000 to 100,000 astronomical units, AU, from the Sun. For context, Pluto orbits at about 40 AU. Voyager 1, humanity's most distant spacecraft, is only around 160 AU from the Sun and hasn't yet entered the Oort cloud, just the outskirts of the Heliosphere. This means the Oort cloud is entirely unobserved directly. Its existence is inferred through the orbits of long-period comets, icy bodies that plunge into the inner solar system from random directions, often with highly inclined or retrograde orbits that suggest they came from far above or below the solar plane. Comets like C2017K2, Pan-STARRS and C1995-01 Hale-Bopp arrived on steep oblique paths that hint at origins in the lower hemisphere of the Oort cloud, its underside. These trajectories offer the best indirect evidence for the three-dimensional nature of the Oort cloud, supporting the idea that it forms a vast spherical shell rather than a flat disk. And that symmetry, or lack thereof, raises critical questions. Is the Oort cloud uniform? Or is the bottom different? Some ideas say that the southern part of the Oort cloud might be made differently because of galactic waves and the Milky Way's mass distribution's gravitational pull. The solar system is not exactly in the galactic plane, it is slightly above it. This means that the Oort cloud is not fully affected by the disk's gravitational pull. Over time, this could make the bottom stretch or contract differently than the top, which could make more things fall in from below. Other disturbances are caused by stars going by. As the Sun moves through the galaxy, nearby stars sometimes get close enough to push items in the Oort cloud out of their paths. Around 70,000 years ago, the star Schultz's star came within less than a light year of the Sun. This was close enough to have brought a wave of comets in, possibly from the lower half of the Oort cloud. The bottom of the Oort cloud could be shaken up a lot by stars like Gliese 710, which is expected to pass within 0.06 light-years in about 1.3 million years. There's also growing interest in how the dark matter halo of the Milky Way may affect this region. Some models propose that dense clumps of dark matter could pass through the Oort cloud, particularly from directions below the solar system, where fewer observational constraints exist. These interactions might dislodge comets or even trigger extinction-level bombardments of the inner planets, though this remains speculative. The things that make up Oort cloud items may also change depending on where they are. If the cloud was formed by planetesimals being scattered around in the early solar system, then the lower hemisphere might have more captured extrasolar material. This means that it contains objects that didn't come from around our Sun, but were grabbed by gravity when they came close to other star systems. These objects may not be the same as comets that are formed by the Sun in terms of their isotopic fingerprints, mineral structures, or volatile makeup. But with no direct imaging and no spacecraft even remotely close to it, how can we learn about the underside of the Oort cloud? The answer lies in tracing inbound comets, studying their orbits, angles, and compositions as they swing through the inner solar system. High-inclination comets with orbits below the ecliptic provide a directional signature of the lower Oort cloud. As instruments like Vera C. Rubin Observatory come online, we expect to discover thousands of new long-period comets, including those from the southern sky. We might be able to send a probe to the edge of the solar system someday. If accepted, ideas like NASA's Interstellar probe could go thousands of AU into deep space, maybe going through or close to the inner Oort cloud and giving us the first direct information about this very old structure. A project like this could measure the amount of dust, the magnetic fields, and the types of particles by comparing the upper and lower regions to see if there are any imbalances. Trajectory into the galactic core from below. Under the solar system's smooth path around the Milky Way lies the galactic core, which is very old, very big, and can't be avoided by gravity. It's the active center of the Milky Way, with thick groups of stars, strong magnetic storms, and a giant black hole called Sagittarius A star. We move around the center of the galaxy in a nearly flat path along the disk, but our gravity well goes above and below that plane. And if you fell from our solar position at an angle, you would start a long swirling trip straight into the core from below. Our solar system is not fixed in the galactic plane. It oscillates, bobbing slightly above and below the midline of the Milky Way every 30 to 35 million years, influenced by the uneven pull of stars, gas, and dark matter. Right now, we sit about 25 to 30 light-years above the galactic midplane, drifting slightly downward. This motion, while subtle on human timescales, is critical to understanding how matter flows through the galaxy, especially how it might fall inward from below toward the center. If you were to follow an object going straight down from where we are, it would first go through the galactic plane, which is a thick area full of stars, gas clouds, and dust paths. The Milky Way's apparent mass is mostly in this area. As you go lower, gravity will start to pull you more closely towards Sagittarius A star, which is about 26,000 light-years away from the Sun. Every light-year, the pull gets stronger, the orbital speed goes up, and the gravity well gets deeper. This isn't a straight fall, of course. The motion is affected by the differential rotation of the galaxy, meaning the inner regions rotate faster than the outer ones. An object falling in from below wouldn't take a direct radial path. It would spiral inward, caught in the swirl of the galaxy's rotating arms and dense stellar populations. Along the way, it would encounter vast regions like the bulge, where stars are older, redder, and packed hundreds of times more densely than in our local neighborhood. What makes a descent from below particularly interesting is that the southern galactic hemisphere, beneath the disk, is less mapped than its northern counterpart. Due to Earth's position and the orientation of many telescopes, the southern sky has historically received less deep sky survey coverage. That's changing rapidly with new instruments in the southern hemisphere, like the Vista telescope and the upcoming Vera C. Rubin Observatory, which will provide critical detail on the southern arc into the core. Along the fall, you'd also pass through giant molecular clouds, magnetic filament zones, and regions of intense star formation, like those in the central molecular zone. The density of matter and radiation increases dramatically. The ambient magnetic fields become more tangled, and the probability of encountering exotic objects, neutron stars, black holes, stellar collisions, rises sharply. At the heart of it all is Sagittarius A star, the supermassive black hole with a mass of about 4.3 million suns. It lies nearly motionless in the galactic center, yet exerts influence over tens of thousands of light-years. Falling toward it from below the galactic disk, you'd enter a zone where gravity warps light and time itself slows down. This black hole is currently in a relatively quiet state, but evidence from the Fermy Bubbles and X-ray flares suggests that it wasn't always so passive. A few million years ago, it may have erupted, blasting material and radiation outward in a pair of massive lobes that still rise above and below the galactic center. Around a black hole, there is a line in space-time called the innermost stable circular orbit, ISCO. If something spirals in from below, it will finally hit this point. After that, it can't stay in orbit, so it will fall in. It is likely that the object would be torn apart long before that, though, by strong magnetic chaos, radiation pressure, and tides. But back in the real world, outside of sci-fi descent scenarios, the idea of vertical infall into the galactic center remains important to astronomers modeling stellar migration, halo evolution, and galactic feedback mechanisms. It helps explain how matter moves not just around the galaxy, but through it, crossing planes and interacting with dynamic forces in all three dimensions. This vertical motion is now included in modern models of galaxy dynamics. This shows that stars and gas don't stay stuck in small slices of the disk. They are spread out over time by supernovae, dark matter clumps, or gravitational resonance, going in orbits above and below the plane and often falling in toward the center. And these vertical flows may feed the center black hole, sending gas clouds that cause explosions that change the way the Milky Way has evolved over time. Micrometeoroid paths from below the orbital plane. Most of the time, we picture meteor showers as flashes of light in the sky. But these micrometeoroids, which are tiny pieces of rock and dust, come from far beyond our atmosphere. Not as well known is the fact that a lot of these particles don't come from above. They come into orbit around Earth and the rest of the solar system from below the orbital plane. They arrive at oblique or backward angles that show the solar system is more three-dimensional than we usually think. The orbital plane of the planets, aligned closely with Earth's ecliptic, serves as our navigational baseline. Most solar system bodies lie along or near it, but micrometeoroids are not limited by this plane. Many originate from cometary debris trails, long strands of material left behind as comets shed mass during close passes to the Sun. And while periodic comets like Swift-Tuttle or Tempel-Tuttle orbit in relatively predictable loops near the ecliptic, long-period comets arrive on steep, highly inclined paths, often plunging from deep space below the orbital plane, depositing debris in their wake. These lines connect to some of the most amazing meteor showers, like the Leonids and Perseids. Earth hits these debris fields at different angles as it goes around the Sun. If the comet's path is tilted, its dust and the micrometeoroids that come from it may be coming in from south of the ecliptic and hitting Earth's upper atmosphere at 20 to 70 kilometers per second. Even though these particles are smaller than sand grains, they are moving so fast that they turn into plasma right away, which is what we see as bright flashes. Micrometeoroids from below the plane don't just hit Earth. They interact with satellites, spacecraft, and the Moon, scarring surfaces, compromising shielding, and triggering impact alarms. In fact, missions like NASA's LDF, Long Duration Exposure Facility, and the European Space Agency's Meteoroid and Space Debris Terrestrial Environment Reference MASTER model have both recorded a non-uniform distribution of micrometeoroid impacts, including directional biases that suggest entries from below. Some of these impactors are part of what's called the zodiacal dust cloud, a torus-shaped band of fine particles orbiting the Sun. While the cloud is densest near the ecliptic, infrared observations from missions like IRAS and COBE have shown that it has vertical structure as well. The dust is pulled by solar gravity and sculpted by planetary resonances, but it's also affected by Poynting-Robertson drag, which causes it to spiral slowly inward. Along the way, inclined orbits intersect Earth's path from both above and below. Interestingly, some micrometeoroid streams may even originate from outside the solar system. These interstellar micrometeoroids travel on hyperbolic trajectories and enter the heliosphere from all directions. Recent detections by Ulysses, Galileo, and Cassini suggest that a measurable fraction of dust particles we encounter come from beyond the Sun's influence, approaching from the galactic south, aligned with the direction of the local interstellar wind. These grains are incredibly fast, incredibly small, and nearly impossible to track, but their entry from beneath the solar orbital plane adds another dimension to the hazards and mysteries of spaceflight. Many micrometeoroids are too small to do damage, but large enough to cause wear over time. On satellites, they erode thermal blankets, scratch lenses, and even puncture solar panels. The International Space Station regularly reinforces its shielding and monitors its orientation to reduce exposure, especially during known meteor stream peaks. During certain showers, the odds of impact from below the plane can rise significantly, depending on Earth's orientation relative to the debris field. To better study and predict these impacts, scientists use instruments like DRAGONS, debris-resistive acoustic grid orbital Navy sensor, and DETECT, which measure impacts in real time. These tools help refine our models of micrometeoroid distribution and their angles of approach, many of which show clear entries from southern sky directions. Future projects that go beyond the ecliptic, like Solar Orbiter or any future probes to the Oort cloud, will have to deal with micrometeorites that aren't found anywhere else in the solar system. More research into where these particles come from, especially those that come from below, teaches us more about the dynamic layering of the solar system. This is where dust and junk don't just circle in a flat pancake, but float, fall, and hit each other in 3 dimensions. Possible gravitational corridors beneath the Sun. Under the well-known patterns of planets' orbits and comets' paths, there is a less well-known structure in space: gravity corridors, which are unseen roads made by the Sun's mass and the galaxy's own pull. These are not real tubes, but mathematically stable paths through space made by gravitational forces interacting in complicated ways. A new study shows that gravitational corridors may also exist below the Sun, giving matter and even spacecraft other ways to move through the solar system and beyond. Most studies have focused on these routes in the orbital plane. These corridors are described by what's called the Interplanetary Transport Network, a system of Lagrange points, stable orbits, and chaotic regions where gravity balances in precise dynamic ways. Around the Sun and its planets, these corridors form webs of potential motion where objects can fall through space with minimal energy input. But most models focus on movement along the ecliptic. What if you shift your focus vertically? What lies beneath? The concept of 3-dimensional transport routes began to gain traction with studies using restricted 3-body problem simulations. These models analyze the gravitational relationship between the Sun, a planet like Jupiter, and a third small object, say an asteroid or spacecraft. The regions of gravitational influence from these massive bodies don't lie perfectly flat. Instead, they form curved 3D surfaces, opening potential pathways above and below the solar plane. In these lower regions, certain gravitational valleys allow for more efficient long-distance travel, similar to riverbeds in a landscape. Recent missions like NASA's Lucy and ESA's JUICE take advantage of these corridors for fuel-efficient travel. These paths often loop through Lagrange points, locations where the gravitational pulls of the Sun and a planet balance out. But now, advanced simulations are revealing how lower-angle gravitational funnels may exist beneath the main orbital plane, especially in regions unperturbed by major planetary masses. This becomes particularly important for understanding how objects like asteroids, comets, or interstellar debris might enter the inner solar system. If a body is nudged from the underside of the Oort cloud, it may not follow a chaotic, random descent. Instead, it could slip into one of these gravitational lanes, guided inward by the solar system's subtle geometry, its trajectory bent not by brute force, but by delicate gravitational guidance. The main thing that shapes these lower paths is the Sun itself. Its mass bends space, and when it comes together with the pull of the galaxy below us, called the galactic midplane, a potential gradient is made. This makes it possible for low-energy paths to go both outward and upward. The worst possible example. In theory, a spaceship could spin beneath the Sun on a hyperbolic escape path, using the pull of the Sun and the planets to help it leave the solar system in the direction of the southern galaxies with little fuel use. There's also increasing speculation that these corridors may have channeled material inward during the early solar system. Billions of years ago, icy bodies and planetesimals scattered from the outer disk may have followed these gravitational routes downward, forming a rain of material that helped shape the inner planets. This vertical infall especially from the southern regions of the protoplanetary disk, could explain certain asymmetries in planetary composition and orbital inclination. It's not always true that gravitational corridors are inactive roads. They can also catch things. Small pieces of space junk may get stuck in paths around the Sun for a short time because of different gravity forces pulling on them. This might help us understand rocks that move in close orbits with each other and groups of dust that stay in strange tilted orbits and are hard to see with our tools. Some of these might even be old artifacts that were moved into place billions of years ago but are still stuck under the plane because of gravity. Understanding and using these gravity pathways will become more and more important in the future. For energy efficiency, future trips to the Kuiper Belt, interstellar space, or even planetary security plans may depend on being able to find and use these secret lanes. There's also a good chance that intelligent civilizations in other parts of the galaxy would use these gravity seams to travel between solar systems without needing huge amounts of fuel, just smart physics. Low-density regions below the local interstellar cloud. There is a faint haze of gas and dust in space that our solar system moves through. It's not just empty space. This is called the local interstellar cloud, or LIC. This cloud is a thin layer of partly charged hydrogen and helium that is about 30 light-years across. It's a part of the local bubble, a bigger group of objects between the stars. However, what lies below the LIC plane, toward the south of the galaxy, tells an interesting story of empty spaces and lost mass. Beneath the solar system's trajectory through the LIC lies a region that is markedly less dense. It's part of what's often referred to as the intercloud medium, zones between the denser, cloud-like clumps of gas that make up much of the Milky Way's disk. These low-density regions can be more than just empty. They can affect everything from the solar wind's shape to the propagation of cosmic rays and radio signals across the galaxy. The LIC has a density of roughly 0.3 atoms per cubic centimeter, surprisingly sparse, but still much denser than the nearly vacuum-like intercloud regions below it, which drop to densities around 0.05 atoms, cm3, or even less. These differences in density are not just academic. They define how the heliosphere, the bubble created by the Sun's solar wind, behaves. When the solar system crosses into a lower density zone, the heliopause, its outer edge, can expand. Conversely, if we move into a denser area, it compresses. Current models suggest that we're actually near the edge of the local interstellar cloud, heading into one of these lower density regions below. If that's correct, it could mean a subtle but measurable change in how interstellar particles and galactic cosmic rays penetrate the heliosphere. These low-density zones are more transparent to high-energy particles, meaning the solar system may soon experience an increase in cosmic ray flux, potentially affecting everything from satellite electronics to long-term astronaut health. But how do we know what's down there, below the LIC, if it's so sparse? Observations of ultraviolet absorption lines, especially from nearby stars located in the galactic south, have been key. Telescopes like the Hubble Space Telescope and Far Ultraviolet Spectroscopic Explorer, FUSE, have detected subtle variations in how starlight is absorbed by intervening gas, helping map out the structure of these interstellar regions. Stars like Alpha Centauri, Altair, and others south of the ecliptic offer sightlines that reveal where the LIC ends and the void begins. Supernovae from long ago shaped the forms of these low-density areas. Multiple blasts in the last 10-20 million years are thought to have destroyed large parts of the interstellar medium. This created the local bubble, a hole that is 300 light-years across. Inside this huge empty space is just one cloud called the LIC. Below it is a spot that is even cleaner, almost like a dead town in space. There are no big clouds or chemical clusters. There is only hot, thin plasma that is ionized and moving between the stars. If future missions like Interstellar Probe or Voyager's successors travel south of the ecliptic and beyond the heliosphere, they will pass into these low-density regions first. The data collected from these journeys will give humanity its first direct measurements of the underbelly of the interstellar environment. The region might be low density, but it's high in scientific value. Even stranger, these gaps may be ways for messages from other galaxies to get to us. Long-range radio signals, whether they are natural or man-made, can pass through more easily when there are fewer particles to spread or absorb electromagnetic waves. Some scientists think that civilizations, if they exist, might choose to put listening stations or transmitters in these low-density passageways so that they can talk to each other more clearly across light years. What lies below the LIC is not chaos or collision, but silence. Space, stretched out thinner than anywhere else nearby. A buffer zone carved by supernova fury and smoothed by time. It is the calm between interstellar storms, and the next chapter in our solar system's long voyage through the galaxy. In the dark southern stretch below, we're heading into the emptiest neighborhood we've ever known, and that, paradoxically, may reveal the most. Cold anomalies in the cosmic background radiation below. Deep below the familiar plane of our solar system is something much stranger than comets or dust. It's something that's built into the universe itself, like a cold scar in the oldest light we've ever seen. This is one of the strangest things found in the cosmic microwave background radiation, or CMB. The CMB is the universe's faint uniform glow after the Big Bang. But uniform doesn't really mean perfect, because there is a much colder area below the galaxy midplane that won't behave like the rest. This area faces the southern sky. Dubbed the CMB cold spot, this anomaly lies in the constellation Eridanus, well below the ecliptic and even further from the galactic plane. It spans nearly 5 degrees across the sky, a massive chunk when you consider the full CMB map, and shows a temperature deviation of around -70 microkelvin compared to the CMB average. That's not freezing by Earth standards, but for cosmology, it's a shiver that sends scientists into a frenzy. The first clues about this strange patch came from NASA's WMAP mission in 2004, and later from the ESA Planck satellite, both of which created ultra-precise maps of the CMB. While some fluctuations in temperature are expected, after all, they seeded the formation of galaxies and stars, the cold spot is too big, too deep, and too statistically unlikely to be dismissed as noise, and its position in the southern galactic hemisphere, away from common sources of interference, gives it even more credibility. So what could be making it so cold below our feet? One theory says it's just a coincidence, just a quantum foam fluctuation that was very big in the early world. But that answer doesn't make a lot of scientists or astronomers happy, even though it makes sense mathematically. It happens way too rarely. Another idea is the supervoid hypothesis. Some believe the cold spot might be caused by a vast underdense region in the universe, an enormous supervoid spanning hundreds of millions of light years. If photons from the CMB passed through this region, they would lose a bit of energy due to the integrated Sachs-Wolf effect, arriving on Earth cooler than they should. Several galaxy surveys have indeed hinted at a large underdensity in that direction, but not nearly large or empty enough to fully explain the temperature dip. More exotic theories suggest we may be seeing the fingerprint of something outside our universe entirely, like a bruise left over from a collision with another universe during the inflationary period. While there's no solid evidence for this yet, it remains one of the most tantalizing explanations, especially given the cold spot's precise alignment and persistence across multiple observational data sets. And yet, there's still another layer to the puzzle. Why the southern hemisphere? Astronomers have noted that many CMB anomalies, not just the cold spot, seem to show a mild preference for the southern sky, particularly beneath the galactic plane. This includes odd alignments of CMB multipole moments and statistical imbalances between the two hemispheres of the sky. While it could be observational bias or instrument calibration issues, repeated cross-checks with different satellites and filters continue to support the existence of real asymmetries. The area around the cold spot is also one of the cleanest places in the sky to observe the CMB because there isn't much cosmic dust or other background noise there. That makes it a great place for cosmologists to try very accurate models of how the universe began and how it is put together. Also, any strange event in this area is taken more seriously because there isn't much else to blame it on. As of today, the cold spot remains one of the most mysterious features ever found in the cosmos. It's a subtle chill, measurable only with sensitive instruments, yet echoing through every equation that tries to explain our origin. And it's located not far beneath the plane of our solar system, forever haunting the cosmic south. Axion and WIMP particle zones below the galactic midplane. There may be answers to the universe's biggest puzzles in matter that we can't see. Some of these secrets may be hidden below the galactic plane, in quiet places where even light is afraid to go. To look for dark matter, scientists have gone to labs deep underground, telescopes at high altitudes, and machines that speed up particles. But there is a new realm below the organized plane of the Milky Way. This is where hypothetical particles like axions and WIMPs may be moving in large numbers that are not well understood. WIMPs, weakly interacting massive particles, are a leading candidate for dark matter, massive particles that rarely interact with ordinary matter except through gravity. Axions, on the other hand, are ultralight particles theorized to solve inconsistencies in quantum chromodynamics, and they too might make up dark matter in huge numbers. Unlike WIMPs, axions could form wave-like condensates and interact weakly with magnetic fields, giving them different behavior in galactic structures. Now look at the Milky Way's vertical outline. This includes not only its spiral arms or curve, but also the thick, disc-shaped area it fills. There is a region below the galactic midplane that is not as affected by star feedback, supernova shockwaves, and radiation storms from the central bulge. This is roughly the uniform center of the disk. Because it is mostly calm, this area may naturally attract cold, slow-moving particles like axions and WIMPs, creating thin but long areas with higher concentrations just below the plane. Simulations of galactic dark matter halos suggest that substructures or clumps could exist not only radially outward, but vertically displaced. These clouds, sometimes referred to as dark matter streams or caustic rings, can intersect the solar system periodically. If one of these dense streams lies beneath our orbit, then dark matter particles could be arriving on upward trajectories, something only a few instruments are positioned to detect properly. Detecting them is no small feat. Experiments like Xenont, Lux Zeppelin, and ADMX are designed to catch fleeting interactions, either WIMPs bouncing off atomic nuclei or axions converting into photons under strong magnetic fields. However, the Earth's rotation and orbital motion mean that detection rates can vary slightly depending on direction, and researchers are beginning to factor in potential anisotropies from galactic vertical motion, meaning some particles could be streaming from below. This becomes even more interesting when you consider our position relative to the galactic plane. The Sun is currently about 20 light-years above the midplane and slowly oscillating downward, part of a 60 million year cycle through the galaxy's gravitational field. This means we are, in effect, falling toward the galactic underlayer, into regions that may contain different dark matter densities or particle flow profiles than the ones we've sampled before. Recent studies have suggested that anomalous seasonal signals detected by experiments like Gamma Libra could potentially be explained by such vertical motion, especially if dark matter isn't perfectly uniform. Some models propose that axions might even form sheets or filaments in these regions, creating directional hotspots of detection below the galactic disk. If these sheets extend below the plane, they may be intersecting Earth at a steeper angle than previously considered. Beyond passive detection, there's also hope of using quantum technologies, such as atom interferometers or superconducting microwave cavities, to look for axion-like particles with better directional sensitivity. One experimental frontier involves pointing these instruments not just around the ecliptic, but directly below the galactic disk, toward the quiet skies of the south celestial hemisphere. These tests might reveal more than just particle physics if they work. They might also show the galaxy's hidden structure. Instead of seeing dark matter as a smooth fog, think of it as a structure under the stars that threads through space like a spider web we're just starting to figure out. Hidden primordial black holes from galactic underside. There may be some of the hardest to find things in the universe down below the galaxy midplane, where sunlight fades and gas clouds disappear into nothingness. These are called primordial black holes. These don't come from dead stars. They come from the chaos of the early universe. Supermassive or stellar mass objects are much bigger than these old objects. They might have been as small as an asteroid or as big as a mountain. They are still one of the most intriguing dark matter possibilities because they are hypothetical, unseen, and very hard to find. There's a chance that some of them are moving below the galaxy disk, where they can hide in the cold darkness. Primordial black holes, or PBHs, are believed to have formed in the first fraction of a second after the Big Bang, when fluctuations in density could have been great enough to collapse directly into black holes. Unlike ordinary black holes that form from supernovae, PBHs could range in mass from subatomic to thousands of solar masses, depending on the scale of those early density spikes. The key is that they could be scattered across the universe like relics, ancient fossils from a time before stars or galaxies existed. But why would we look for them below the middle of the galaxy? This is where the mechanics of the galaxy come in. Dark matter, rogue stars, and even black holes move in long, slow paths above and below the midplane because of the Milky Way disk's gravitational pull. Smaller objects like PBHs could be caught in vertical orbits that are similar to the Sun's, which goes up and down every 60 million years. If there are primordial black holes in the galactic halo, some of them would easily pass through or stay below the galactic plane, especially in places where thick gas and active stars don't get in the way. These southern corridors of low stellar density are ideal hiding places. Far fewer stars and supernova remnants means fewer background signals. That makes subtle gravitational effects easier to spot, if you know what to look for. PBHs don't shine or reflect light, but they bend it. One of the main tools in the hunt is gravitational microlensing, where a PBH passes in front of a distant star and temporarily magnifies its light. Several ongoing surveys, like OJUL and the upcoming Vera C. Rubin Observatory, are scanning the sky for such blips, and the clean, sparse star fields below the galactic plane are a perfect lab for it. But there's more. If a PBH went through or got close to our solar system, it wouldn't just bend light. It might also change the way orbits move in small ways. Small changes in the paths of asteroids, strange pulling on spaceships, or even changes in the spread of dark matter itself could be signs that they are there. We might only be able to tell if a PBH was going below the ecliptic if we compare very accurate models of how the Sun moves over time. Another potential clue comes from gamma-ray background studies. If PBHs are evaporating slowly via Hawking radiation, a theoretical quantum effect, they might release faint gamma-ray signals. The southern galactic hemisphere, with its cleaner foregrounds and less noise from galactic bulge activity, offers an optimal region to hunt for such low-level emissions. Some researchers have even speculated that unexplained gravitational waves, like those detected by LIGO and Virgo, might be the result of collisions between primordial black holes, potentially occurring in underdense regions far from star clusters. If PBHs tend to cluster in low-density zones, the galactic underside may be a hotspot for mergers we can only detect through spacetime ripples. If PBHs are even a small part of dark matter, then as Earth moves around the Milky Way, it may go through streams or groups of them. Since we are currently above the galactic midplane, we are going lower, which means we are entering areas below the disk that may have gravitational shocks. We might never see a primordial black hole, but we could feel it, in warped light, in disrupted orbits, in ghostly gravitational waves echoing from the deep. Somewhere below, in the dark ocean beneath our galactic floor, these ancient objects could be drifting silently, unchanged for billions of years. The search for magnetic monopoles in lower space regions. Physicists have been looking for the magnetic monopole, a ghost particle that, if found, would change the way we think about electromagnetism. A bar magnet always has a north and south pole, but a monopole would only have one, either a north or a south pole by itself. Even though they have never been seen directly, their presence is accepted by a number of advanced physics theories, such as grand unified theories, GUTS, and some forms of string theory. Then where could we find one? One place that looks good is the lower, quieter space below the path of our Sun, which is far from dense matter and noisy magnetic disturbances. Magnetic monopoles are believed to be incredibly rare, potentially produced in the first microseconds of the Big Bang, much like primordial black holes. If they exist, they'd be massive, possibly thousands of times heavier than a proton, and would interact strongly with magnetic fields. But because they're so heavy and slow-moving, they wouldn't zip around space like cosmic rays. Instead, they'd drift, pulled along by the galaxy's magnetic field lines like beads on invisible strings. Below the midplane of the galaxy, the density of stars and interstellar plasma drops significantly. This means there's less magnetic noise from supernova remnants, radio bursts, and solar wind turbulence. In these calmer regions, long-range, coherent magnetic fields become easier to isolate. And if magnetic monopoles are following those fields, that's exactly where we should look. Essentially, if the galaxy is a magnetic spaghetti bowl, the southern hemisphere might be one of the cleanest strands. Scientists are already watching. Instruments like IceCube in Antarctica and Antares in the Mediterranean have searched for signs of monopoles by monitoring deep water or ice for rare ionization trails. But many models suggest that magnetic monopoles might prefer space-based detection, especially outside the heliosphere, where the Sun's own magnetic field isn't masking their signatures. A spacecraft stationed below the ecliptic, facing toward the galactic South Pole, could be in prime position to catch a slow-moving monopole drifting in. Superconducting loops are another way to do it. If a monopole went through them, they would cause a lasting change in the current, kind of like a cosmic toll gate. One day, these loops could be put on robots that are sent beyond the solar system and pointed downward into the less busy, lower galaxy latitudes. This would give a better view of any strange things that happen. Some theorists even propose that monopoles might become temporarily trapped in planetary magnetic fields, or even within Earth's magnetic tail, only to be released during geomagnetic storms. But in interplanetary space, especially in the dark zone beneath our orbit, they'd be more likely to move uninterrupted. That's why future deep space missions may include magnetometers tuned specifically to catch their trace. Why does this matter? If magnetic monopoles exist and can be detected, it would confirm predictions made by high-energy physics decades ago. More importantly, it would explain why electric charge is quantized, why all electrons, for instance, have exactly the same amount of negative charge. That fact, bizarre as it seems, could be the direct result of magnetic monopoles existing somewhere out there. They don't just balance equations. They hold the secret to why the universe behaves consistently at all scales. No real discovery has ever been made so far, but the quiet, cold, and magnetically clean areas in the south of space are still one of the last places they haven't been found yet. Somewhere in that cosmic basement are hidden mysteries. One of them might hold the key to bringing all the forces of nature together. Galactic disk rotation and vertical kinematic flow. As we learn more about it, the Milky Way is not a fixed structure. It lives, moves, and flows through space. Most of us think of the galaxy spinning as a flat spin, like a record player. There are, however, much stranger things to find when you look deeper, especially below the galactic plane. These are vertical kinematic flows, which are movements that rise and fall through the disk like waves in a gravity ocean. And these flows, which happen below the circle of the solar system, may hold important clues about how the galaxy moves and the unseen matter that shapes it. The galactic disk rotation is at the heart of this movement. This is a broad motion in which gas clouds and stars circle the galactic center at hundreds of kilometers per second. The disk is not smooth, though. Tidal forces from galaxies like the Sagittarius Dwarf and the Magellanic Clouds cause it to bend, break, and shake. Not only do these disturbances change the horizontal plane, but they also cause vertical movements that push stars and interstellar matter up and down through the disk, especially near its ends and outskirts. This means that below the galactic midplane, where we often assume stillness, there's actually a slow-motion ballet of matter flowing downward, then rebounding up again. It's like a breathing rhythm hidden inside the galaxy's spin. In 2018, data from the Gaia Space Observatory revealed vertical motions in the Milky Way that shocked astronomers. Stars were found to be moving not just along their orbital paths, but also perpendicular to the disk, undulating in waves that stretched thousands of light years. One interpretation: the galaxy had suffered a cosmic impact, possibly from the Sagittarius Dwarf galaxy punching through the disk billions of years ago. The echoes of that collision are still traveling through the stars, like ripples in a pond. And those ripples flow through the galactic underside. These vertical movements aren't just random. They show coherent patterns that span entire regions of the disk, suggesting the influence of massive unseen structures. Some researchers think they could even be tracking dark matter subhalos, invisible clumps of matter that gravitationally stir the disk from below. If a dense dark matter object passed underneath the plane, it could send shock waves through the disk that we detect as vertical flows. In that sense, the galactic floor may be telling us what's beneath it, without us ever seeing it directly. For our solar system, which orbits the Milky Way every 230 million years, these vertical flows matter. We're not fixed in the disk. We oscillate up and down through it. Right now, we're about 20-25 light-years above the galactic midplane, slowly descending into the southern side. That means in the next few million years, Earth and its neighbors will pass through the thickest part of these vertical waves, possibly exposing us to changing radiation levels, increased comet interactions, and gravitational anomalies. Some theories even tie these vertical motions to periodic mass extinction events on Earth. If our oscillation through the galactic plane exposes us to denser comet clouds or changes in the flux of cosmic rays, it could disrupt the solar system's stability in subtle but catastrophic ways. And that instability would come from below, from vertical flows nudging the balance of space just enough to shift planetary fate. Detecting and modeling these flows is a cutting-edge field. Future surveys like the Vera C. Rubin Observatory and space telescopes like Euclid may help map them in 3D with unprecedented clarity. The goal is not just to chart the Milky Way, but to uncover the forces and impacts that ripple vertically through it, especially those emerging from beneath our current galactic latitude. The galactic disk isn't a flat sheet in the end. There are pulses going through it, and it has its own beats. The kinematic waves keep going deep below that spinning record. They carry secrets, scars, and signs from galactic crashes, unknown masses, and the slow churn of cosmic time. Detection of dark matter currents below the system. All the signs point to dark matter being real, so it's not just sitting there, it's moving. Listening to, moving. According to some very strong ideas, there are currents of dark matter moving below our solar system and running through the galaxy like unseen rivers. They're not visible, we are not allowed to touch them, but we might be able to find their gravity signatures, and they might be much more organized than we thought. Dark matter accounts for about 85% of the universe's mass, yet it remains entirely invisible to electromagnetic radiation. That means we can't observe it directly, but we can infer its presence through its gravitational effects on visible matter. Galaxies spin faster than they should. Clusters hold together against the odds, and on a smaller scale, dark matter may be flowing through and around our solar system in a set of streams or filaments, formed by the galaxy's early structure and its long cosmic dance with satellite galaxies. These dark matter currents, sometimes called tidal streams, are the debris of smaller galaxies consumed by the Milky Way over billions of years. As these galaxies were torn apart, their stars and dark matter were flung across the galactic halo. Many of those remnants now form coherent flows, some of which may be moving beneath the galactic plane, where they are less disrupted by supernovae and stellar feedback. The S1 stream is one of the most well-known possibilities. It is thought to be the remains of a long-lost dwarf galaxy. Simulations show that streams like S1 may enter the solar system from different directions, some from above and some from below. These streams move relative to the dark matter ring of the Milky Way, making a wind of particles that blow past Earth. If there is a stream coming up from below, our planet may go through it more than once during its rotation. Why does this matter? Because dark matter detectors on Earth, like Lux Zeppelin, Xenont, and Super CDMs, are incredibly sensitive to the directionality of incoming particles. Most searches have assumed a smooth, isotropic background, but if dark matter is clumped into streams, especially vertical ones from below, then that directionality can be used to enhance detection sensitivity. Imagine aiming a sail not into random wind, but into a steady breeze you know is coming. There's also another reason to look below. At this point in time, our solar system is moving toward the galactic center, which is in the southern part of the Milky Way. We are probably entering organized dark matter flows that are below that plane. These flows could be made up of remains of tidal debris, collapsed filaments, or even gravitational caustics. In fact, some of the seasonal changes seen in tests that look for dark matter, like those described by the Dama Libra project, may be caused by Earth moving through layered flows of dark matter, some of which could come from below the ecliptic. Adding to this intrigue is the potential of gravitational wave detectors like LISA, the upcoming space-based observatory. Though not built to detect dark matter directly, these instruments might sense anomalous gravitational perturbations caused by dense dark matter currents passing nearby, especially those flowing upward into the solar system's lower hemisphere. But perhaps the most exciting possibility lies in the next generation of directional detectors. These devices don't just detect particle hits, they record the trajectory of each interaction, allowing scientists to map incoming dark matter flow across the sky. If future readings show a consistent dark matter wind rising from the southern sky, it could point to a hidden current flowing upward from beneath the galactic plane. Quiet, invisible, but powerful. It's like discovering an underground river in the middle of the desert. We didn't know it was there until we watched how the ground shifted, how things moved, how gravity itself tugged ever so slightly. And that's the essence of dark matter detection in these southern regions, not seeing, but sensing. Neutral hydrogen layers beneath the galactic plane. Neutral hydrogen is one of the most common but little known parts of the universe. It covers the bottom of our galaxy like an unseen sea. It isn't bright like stars or loud like quasars. A frequency of 1420 MHz makes it hum. The most interesting parts of this hydrogen gas are found below the galactic plane. They quietly record the history of the Milky Way's gravity tides, star formation, and past collisions. Neutral hydrogen, or HI, is hydrogen in its unionized form, just a single proton and electron hanging out together. While individual atoms are undetectable, large clouds of HI emit radio waves at a very specific wavelength called the 21 centimeter line. This signal has become one of astronomy's most powerful tools. By tuning into it, astronomers can map vast hydrogen structures even in parts of the galaxy we can't see with optical telescopes. And one of the most fascinating places to look, below the galactic midplane, where things grow quieter, colder, and more pristine. Radio surveys, like those from the HI-4PI and Galpha-Hi projects, have shown that hydrogen isn't evenly distributed. Beneath the disk, layered clouds of neutral hydrogen extend for thousands of light years. often in warped wave-like patterns. These aren't static, they're in motion, shaped by the galaxy's rotation and vertical gravitational forces. Some of these features form part of what's called the galactic warp, a bending of the disk that curves downward on one side and upward on the other. Our solar system is currently moving downward into this bend, meaning we're heading straight into one of the thickest regions of southern HI concentration. Why does this matter? Because neutral hydrogen is the raw material for star formation. Before there are stars, there are hydrogen clouds, cold, dense, and slowly collapsing. Studying the HI layers beneath the galaxy gives us a kind of time-lapse history of stellar evolution, especially in quieter, low-metallicity environments where ancient processes are still at work. These hydrogen layers often trace out past galactic collisions like scars in the gas. Streams of HI stretching beneath the galactic plane may be residual debris from dwarf galaxies like the Sagittarius Dwarf or the Magellanic Stream, torn apart by the Milky Way's gravity and dragged downward over billions of years. These streams continue to move independently, and their interactions with the lower galactic halo create shock waves, compression zones, and temperature gradients, all of which can seed or stall future star formation. Then there's the puzzle of high-velocity clouds, which are made up of chunks of neutral hydrogen moving at speeds that don't make sense for the galaxy to be rotating. A lot of these are below the plane, and it's still not clear where they came from. Are those pieces left over from old collisions, gas from past starburst winds coming back to the disk? Or could they be hydrogen from other galaxies that is being pulled in from the cosmic web and moving slowly into the galaxy like rain? Astronomers are particularly interested in a feature known as the Smith Cloud, a massive object of neutral hydrogen on a collision course with the Milky Way, approaching from below the plane. It contains enough gas to form 1 million suns and is traveling at nearly 240 kilometers per s. When it merges with the disk in tens of millions of years, it could trigger a burst of new stars in the southern galactic hemisphere. But even before that, the shock waves it sends through the lower hydrogen layers may give us key insights into how gas behaves in deep, cold space. As technology improves, telescopes like the upcoming Square Kilometre Array, SKA, will offer even finer detail, mapping these hydrogen layers in 3D, tracking their movement, density, and interaction with cosmic rays and magnetic fields. It's a bit like scanning the ocean floor of the galaxy, sediment layers, fossils, and buried rivers, all telling stories of what came before. As we look up at the bright stars and nebulae, there is a world below us that is quiet and full of ghostly hydrogen fog that whispers across the radio spectrum. It's what galaxies are built on, what stars are made of, and everything that has ever drifted down into the Milky Way. Voyager probe's exit paths below the heliospheric plane. The Voyager 1 and Voyager 2 spaceships were launched in 1977 with the goal of exploring the big planets, but they've ended up doing something much more important. These robot messengers have become the first real humans to fly into deep space. They have gone beyond the sun's influence and into the unknown. Also, it's interesting that Voyager 2's path to the surface took it south, below the heliospheric plane. This gave us our first real look at what's below the safe bubble of the solar system. To understand why this matters, let's first look at what the heliosphere is. It's a vast bubble carved out by the sun's solar wind, an ever-expanding stream of charged particles that push against the interstellar medium. This bubble shields the planets from a large portion of incoming cosmic rays and external galactic particles. But it doesn't expand uniformly. It's shaped like a teardrop or comet, flattened and warped by the solar system's movement through the galaxy and by pressure from the local interstellar cloud. That means the edges of the heliosphere are asymmetrical, and the exit points of Voyager 1 and 2 offer clues to that shape. Voyager 1 left the heliosphere in 2012, heading north relative to the ecliptic. It entered interstellar space in a region heavily influenced by solar magnetic fields, and though the transition was remarkable, it was turbulent and somewhat ambiguous. Voyager 2, on the other hand, exited in 2018, southward, about 30 degrees below the solar plane. What it encountered was subtly but significantly different. Beyond the heliopause, which is where solar wind stops being the main force, the plasma density was higher in the south. It looked like the magnetic field was also smoother and more steady. It seems that the area between the stars below the system is either thicker, colder, or just less affected by solar activity. It's possible that Voyager 2 went through a quieter tunnel, which would have made it easier to get accurate readings of the space between the stars. In a way, it took a sample of the cosmic undercurrent that runs right below our orbital area. Both Voyagers are now more than 15 billion miles from Earth, but it's Voyager 2 that continues to provide a more stable data stream, largely due to its trajectory. And that's important, because future interstellar probes, like NASA's proposed Interstellar Probe mission, are looking southward for exactly this reason. If you want to escape the noise of the solar system and get clean readings of interstellar particles, dust, and cosmic rays, going below seems to offer a straighter, calmer path. The choice of Voyager 2's southern trajectory wasn't random. It was designed to encounter Uranus and Neptune, which required a downward tilt. But it ended up revealing something crucial. The southern Heliosphere, the region just before interstellar space, might be thinner and more uniform than the northern one. This changes how we think about our solar system's interaction with the galaxy. We're not sitting in a symmetrical bubble, we're in a warped shell, and that shell stretches differently depending on which way you go. There's also the intriguing possibility that Voyager 2 is heading toward regions of higher interstellar particle density, areas that could affect everything from spacecraft propulsion to the stability of future deep space communications. Understanding what lies beneath our system is no longer theoretical. We have a probe out there, drifting silently downward, taking readings from a realm no human has ever visited. And as long as its tools are still working, it will keep sending back information, not just about where it is going, but also about what the space below our solar system is made of. Voyager 2 is making a picture of the southern region, one particle at a time and one wave at a time. Even though we're still hearing, we can start to figure out what it means. Directional anisotropy in particle flow from below. Even though space is thought to be like a vacuum, it is not at all still. Cosmos rays, neutrinos, and ions are all high-energy particles that move in all directions through the galaxy, but not all the time evenly. In fact, some of the most sensitive instruments on and near Earth have picked up on a strange cosmic whisper, particle flow that isn't going in the same way. It's also interesting that a measured part of this flow seems to be coming from below the circular plane of the Sun. Anisotropy simply means unevenness, and in this case, it refers to the fact that particles don't arrive uniformly from all directions. Instruments like the Ice Cube Neutrino Observatory in Antarctica and cosmic ray detectors on satellites like Pamela and AMS-02 have consistently detected slight excesses and deficits in incoming particles depending on where you look. And when the data is mapped out in full sky distributions, you begin to notice something strange. Some of the highest energy particles are coming from below, from southern galactic latitudes. This bias, in one way, isn't just noise. It's statistically significant, and in some cases, it has stayed the same over years of study. Thus, it's most likely a real part of the nearby galaxy, and not just a sensor error or a result of Earth's magnetic field. But why would this asymmetry happen? One possibility is that magnetic fields in the galactic south are configured in a way that funnels or deflects particles upward into the solar system. Cosmic rays, especially lower energy ones, are heavily influenced by magnetic fields. If the southern galactic hemisphere has denser field lines, fossil shock waves from past supernovae, or coherent plasma structures, these could create preferred channels for particles to travel along. Think of it as a subway system for cosmic radiation, except invisible and moving near the speed of light. Another possibility? Remnants of past galactic collisions. The Milky Way has swallowed smaller galaxies in its past, leaving behind debris streams, some of which extend beneath the galactic plane. If those remnants include active black holes, collapsed cores, or even dense dark matter clumps, they could act as particle accelerators, flinging high-energy particles upward toward us. This would explain the observed anisotropy in cosmic rays coming from the galactic south. And let's not forget the role of our own solar system's movement. We are currently headed downward through the galactic plane, meaning we're moving toward this southern sky region. That motion creates a kind of kinetic frame shift, where incoming particles from below appear slightly more energetic, simply because we're moving toward them. It's similar to driving into a rainstorm. The raindrops seem to hit harder from the front, even though they're falling evenly. This effect, known as Compton-Getting anisotropy, can magnify directional differences and help researchers isolate real flow patterns from observational bias. By comparing measurements from instruments in both hemispheres and over long time frames, scientists have begun constructing 3D maps of particle flow in and around the solar system, highlighting that beneath our feet lies a more active region than previously believed. There's also an eerie consistency between these particle anisotropies and other signals, like gamma-ray gradients detected by the Fermi Gamma-Ray Space Telescope and neutrino bursts measured by IceCube. Several of these high-energy indicators appear more frequent or intense in the southern sky, just beneath the plane. Could this be a coincidence? Maybe. Or maybe it's a signature of hidden sources, active remnants, magnetic caustics, or even unknown astrophysical structures lurking below. The implications go beyond curiosity. Understanding directional particle flow helps us build better space weather models, critical for future deep space missions. It may also provide indirect clues about the distribution of matter and energy in the galaxy, particularly in hard-to-observe southern regions. And if there are unknown particle accelerators operating beneath the plane, they could be windows into exotic physics, from dark matter decay to unknown galactic phenomena. So while we often focus our telescopes and detectors on the grand scenes above, the space below is sending us particles with stories to tell. Stories of movement, structure, and perhaps even threats or clues from parts of the galaxy we've barely begun to chart. Tidal effects from galactic masses beneath our orbit. For most of us, tidal forces mean seas being pulled by the moon's gravity, or stars being stretched by black holes. But gravity doesn't just change the shape of things close to it. It also stretches space out over huge distances, making small changes even over tens of thousands of light years. And in the southern parts of the Milky Way, below our solar system, there is more and more proof that the tides caused by galactic masses are changing how we move, how the stars move, and maybe even the shape of the galaxy itself. The Milky Way is not a static disk, it's a dynamic, rippling structure, constantly responding to internal instabilities and external gravitational nudges. One of the largest of those nudges comes from massive structures beneath the galactic plane, particularly from the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy that is currently being devoured by the Milky Way. Its orbit plunges through the disk in a tilted elliptical path, and each pass causes gravitational disturbances that ripple across the disk like a stone hitting water. These disturbances are strongest in the southern sky, beneath the galactic plane, where the Sagittarius dwarf has left behind streams of stars, gas, and dark matter. As it orbits, its mass exerts tidal forces on the lower half of the Milky Way, subtly pulling on stars and stretching the dark matter halo. That includes us. Our solar system is currently descending toward the galactic midplane, and some models suggest that our vertical motion may have been partially triggered by this ongoing tidal interaction. But there's more than one dwarf galaxy left. Even bigger are the Magellanic Clouds, which are two uneven satellite galaxies that circle below the southern disk of the Milky Way. It is thought that their combined gravity pulls dark matter and bends the Milky Way's outer ring, making a gravitational wake. This drag makes the halo uneven and causes vertical movements in the galactic plane. These wobbles move through the stars, gas, and maybe even the tracks of interstellar probes like Voyager. These tidal effects are not just theoretical. Recent Gaia satellite data, which maps the positions and motions of over 1 billion stars, has revealed vertical waves in the Milky Way's stellar disk, some of which rise and fall over thousands of light years. These patterns, sometimes called galactic seismology, suggest that the disk is vibrating in response to ancient tidal impacts, many of which originated from below the plane. What does this mean for the Sun and planets? It means the ground below us isn't still. Large galaxies, dark matter clusters, and the Milky Way's own southern region are all pulling on it in a tug-of-war battle of gravity. These forces can make our path move back and forth, change how the stars around us move, and even change where interstellar clouds are located, which changes how fast stars are formed. Some researchers believe these vertical movements, rising and falling through the disk, may follow a cycle of around 60 to 70 million years. Interestingly, this timing lines up with several mass extinction events on Earth. While the link is speculative, the theory suggests that as the solar system bobs through the galactic plane, it may pass through denser regions of cosmic dust or experience more intense comet bombardments, potentially influenced by tidal debris stirred up from beneath. Tidal forces from below might help explain the asymmetry in galactic warp, why the southern part of the Milky Way bends differently than the north. The tidal drag from galaxies like the Magellanic Clouds isn't just warping our disk, it's warping our models of how stable galaxies are supposed to be. As we continue mapping these gravitational influences, simulations grow more complex and more stunning. What they show is that gravity from below doesn't just pull, it reshapes, it sculpts, it causes stars to shift, dark matter to cluster, and entire gas clouds to ripple outward. And we are not immune to its touch. From dark matter filaments arching over our heads to icy Oort remnants buried in the galactic deep, the vertical frontier is far from empty. It's a dimension packed with forces and anomalies that might hold the next great answers in astrophysics. If this documentary expanded your view of the universe, don't forget to like, subscribe, and ring the notification bell. We've only just scratched the surface of what's out there. This is Beyond Horizons, and we'll see you on the next mission into the unknown.